in 2026. So the judging will be in Vienna, Austria. But of course, the submission will be like a year before that. So for the deadline for the next one, it's not yet been announced, but I do suggest to look at the iforce.org website. So there is a particular section there, iForce Prize for Development. No. So but of course, no, it's not a requirement. But of course, if ORSI is a member of iForce, and if you are a member as well of ORSI, then yeah, that could help, but I don't think it's a requirement. Thank you, ma'am.
Any other question? Then we must thank the speaker once again. Thank you, sir.
So, sorry, this iForce support. Sorry, I didn't get the question.
Sir, I'm asking something about the project. International operations project proposals from different participants from different countries. So, is option for iForce project proposal from international participants?
Direct question is there any possibility of getting funding from IFRS for carrying out project in India? Am I right?
Okay. So for now, I'm not aware of any. So far, what we support is just the prize in development, but the one I also mentioned, the Orfest. So this is the like the school that's set up with different participants, and these are partly sponsored as well. But for specific projects right now, so this one maybe I will check with the administrative committee if we can do so in future. But for now, I'm not aware. Yeah. Thank you. Okay. Thank you so much.
So the next speaker is Professor Gautam Chakraborty. Yeah,
so when I
So I just read out a few lines for him, his resume. So Professor Gautam Chakraborty received his PhD in 1993 from Tohoku University, Japan. Before joining Tohoku University, he worked in communication industry in India. From the past 20 years, he was professor and head of the Intelligent Informatics Laboratory, Department of Software and Information Science, Iwata Prefectural University, Japan. His research interests are machine learning, soft computing algorithms, deep neural networks and their application to solve pattern recognition, prediction, scheduling, and optimization problems, including applications in wireless and sensor networks. He is interested in the analysis of various time series signals like ECG, EEG, and other biosignals for health or medical applications. He is also interested in data mining and text mining. So thank you, sir.
yeah, thank you. And thank all of you who has come to participate in this session. Basically, I mean, if you see the title of this conference, it's optimization, learning, and then analytics in business. Okay, I do work in optimization because, and in fact, neural network training, they're actually optimizing something. Okay. Most of the problems we do, finally, it can be defined in terms of some optimization problem. But in this talk, and I do work a lot in data mining and data science, but today my lecture is on basically on learning. Okay, and the application area is computer-aided diagnosis, medical healthcare. And the problem is object detection. Object detection means, starting from auto driving and computer-aided diagnosis, all are object detection, but of different various types. Okay, and sometimes you have to detect the object, and its location is more important. For example, if you're driving a car, then your object is not on the road, like your object is a human body, but not on the road. It doesn't make, the things that you need to care about. But if the object is on the road, so the position, the detection of a particular object and the position is important. In case of medical data, especially medical image data, we need to check whether the object is there or not, and then if the object is there, what is its class? Okay, so like a cell image, it could be a healthy image or it could be a cancerous image. So you have to classify whether the object is there, and if the object is there, what is this class? Okay, so this talk is basically regarding that. And I'll emphasize on the learning part, and then I'll also emphasize on the difficulties of, convincing the medical doctors the machine learning algorithm, and sort of tell them that the way you are, the level of detection that you do and the level of detection we do using machine learning, they're almost same, or sometimes it's better. Okay, but that is a difficult issue. I worked in, I still work actually in Iwate Prefectural University, and I have an office there, and I visit and I take class sometime. But recently I joined a private university exactly like Heritage, somewhere very near to Bangalore. So we fly between, Bangalore and Japan quite often. The title of my talk is Object Detection and Classification in Computer-Aided Diagnosis. If you work with deep neural network, you can see that most of the models are there. And in fact, most of the models are already pre-trained, but still the choice of the model and the choice of your feature, that makes a lot of difference in the quality of the detection. So those things also I'd like to emphasize. How much time I have exactly? Huh? 45 minutes. 45 minutes. A little less. Yeah, I know. Okay. So I'll finish by 1:20 or 1:25, right? Okay. Huh? Oh, no, it's okay. It's okay. So this is about some, what I should say, peripheral talk, which I'll skip. And this says that healthcare system really needs some, machine learning assistance, especially in countries like Japan, where you have lots of equipment. MRI machine or CAT machine is available everywhere, even in a small clinic. But good doctors are not available, especially if you go to remote places. Okay, so it's very easy nowadays to take the picture and then send it to some center, and the doctor do diagnosis there. But if you can do some preliminary diagnosis at the remote place, and then only when there is a sort of risk, then only you send to the expert. That type of things are getting popular in countries like Japan, where the equipments are there, but the scarcity of doctor is everywhere. Okay. Yeah, and I want to emphasize here that though I mean computer-aided diagnosis has now achieved a level of detection almost same as an experienced doctor, but the black box design of the deep learning is sort of, I mean, difficult for the doctors to get convinced that, okay, this is working the way we work, okay? And another thing is that the treatment regime, I'm not sure, I think in India also it's like that. From hospital to hospital, the way the treatment process or even the diagnosis process, that's different. And of course, I mean, you must know that from state to state, it is different. And it's difficult for a machine learning algorithm to adapt to that, because machine learning algorithm gets the data, and if the data is from the same hospital, then that training will also depend on how the doctors in that particular hospital thinks or diagnose, okay? And but when you send them as a product, you have to have some generalized sort of prediction decision algorithm. Okay, so that is a big problem. And today, though the talk will basically be on the learning method and things like that, I will use a particular example, and that is HCC. HCC is actually liver cancer. And it's one of the difficult problems in the sense that if you have liver cancer, you don't realize it till at the very end, okay? And when the things are, I mean, out of control, okay? So the early detection of the liver cancer is very important. But early detection, the problem is that the change in the cellular structure is, I mean, very subtle. Even for doctors, sometimes difficult to, I mean, diagnose properly. So actually for liver cancer, if you take the liver biopsy image, there are 5 stages. Stage 0 means it's a healthy biopsy image, and stage 4 means it's in a metastasis. I mean, the cancer is full blown. Okay, but if you detect in the stage 1 or stage 2, which is called the early stage of cancer, it's curable. If it is detected in stage 3 or stage 4, it's very difficult to prevent metastasis. Okay, so not only that, you have to detect the cell structure, but you have to classify it properly for these 5 different classes 0 to 4. Okay. Okay, so this is the agenda. It's okay, and then if you see, I mean, it's difficult to see from far, but this is grade 0 means it's a healthy, and it is grade 4, which is, I mean, a very later stage of cancer. Okay. Till now, most of the diagnosis was based on the cell structure. Actually, if you see the biopsy image, it's a cell and the nucleus. Okay, the nucleus structure gives a lot of information about the stage of the cancer. But so that's a classification problem. You have to detect the nucleus, and then from the nucleus structure, you have to classify whether it's a stage 0 or stage 4 or like that. Okay. And that was the prevalent method of using computer diagnosis for liver cancer. What we added is that not only the cellular structure, but also the, I mean, the pattern, the overall pattern of cytoplasm. Okay, that is also very important. Okay, so we call almost all researchers prior to us, they use only the nucleus feature, which I call local feature. But the nucleus arrangement how the different nucleus or different cells are arranged within the BAPS image. And that also gives a very important, decision to decide whether it's a later stage or earlier stage. Okay. So we added this global feature, and by adding that, we could improve the accuracy by a, greater margin. Okay, and we could publish it in an IEEE journal. So these are the different nucleus features, which here is another point which I want to emphasize, is that these are the nucleus features which the doctors look at. But as you know that when you use deep neural network, in the first stage of convolution neural network, we extract features. What features are exactly extracted, that you don't know, because it's a black box, okay? And the problem to convince a doctor that what features we are extracting is exactly the same what you are doing, it's impossible. Because actually, as a machine learning expert, also we don't know what features are actually extracted, okay? So one part of our work is to sort of make the deep neural network a little white instead of a black box, to make it a little white, in the sense that the features we are extracting can be visualized and things like that. Okay, and these are the features that the doctors look for from the nucleus structure. I'm not going into the detail. And what they do is that extract the feature, and then they do the classification, and they say, okay. So most of the works previously done is that this is a whole, BAPS image. They usually separate into different, mesh-like structure, and from there they take the nucleus and they detect and do some voting and give some decision. Okay. This part I will go very quickly. This part says basically about the segmentation of the nucleus. Okay, so this is the image, and if you see the green boxes, they are the segment where the nucleus is there. Okay. In addition to the nucleus, there are many other, particles which are present in the biopsy, but our intention is to extract the nucleus part only. So this boundary detection is an important issue. Not only that, depend on the image, these nucleus images could be blurred or it could be sharp. Okay. If you see, this is a healthy image where the boundary is very clear and almost spherical. And this is stage 4 cancer, where the boundary is not clear and the structure is sort of, not circular like that. Okay. And in case of blood, it is still very difficult to find the boundary. So boundary detection itself is a problem. But in this talk, I'll skip that portion. Okay. Now, this is the result of the previous work, where they extracted the nucleus part, and based on the nucleus features, they predicted the cancer. So basically, it's like that. You have a biopsy image, you extract all the nucleus, then you classify them, and then depending on the voting. So if in a biopsy image, usually you have 200 to 400 nucleus. So out of 200 nucleus, suppose 150 are class 4, then the decision is this is class 4, because most of the nucleus belong to class 4 category. If you do that like that, then you are, working only with the local nucleus image. Okay. So what we claim is that is not sufficient. We have to have the image, a global, pattern of the biopsy image. And you can see here the red are the mistakes. Okay, though originally it is a G3 image, 18 of that was classified into G4 category, grade 4 category. Grade 4 means very grave. Okay, and this is our method. And instead of course, we do nuclear segmentation. And then we also use the image part. Okay, so as an input to this is okay, this is okay. I think this maybe I should discuss a little. Here, what do you want to emphasize? Just a moment, okay. Yeah, here what I want to emphasize is that when you extract, when you do the boundary detection, in addition to the nucleus image, there are some other, particles which are available in the blood or in the cell. They are also extracted. Now we have to separate, because this doesn't give any indication, or this doesn't help in the classification process. So what we do is that in the first stage, whatever we whatever we filtered out by boundary detection, out of that, maybe out of 100, 80 are nucleus images, but the rest is something different, which we first want to filter out. And that filtering out process is described here, that we do by using some unsupervised learning, clustering, okay? And that detail again will take some time to give the detail, but basically in this process what we do is that we eliminate all those which are in the boundary, and most of the images are nucleus, so those which are in the center, they are actually from the nucleus image, so we retain that. This filtering process detail I'll skip, but we do some filtering, okay. And this is, whenever you do some classification, supervised or unsupervised clustering, you need to extract the features, okay. So this is about how we did the feature extraction part using convolution neural network. And in this convolution neural network, we use DenseNet. And the original convolution neural network was only feed forward like this. But in DenseNet, there are some jumping connection from output from here, also goes here, also goes here, also goes here. In that way, no feature extracted till now is being left out, okay? So all the features from different layers of abstraction are added so that we have a richer feature when we go to clustering or classification anyway. And this is the main slide which distinguishes our approach from the previous approaches, okay? So here we take the nucleus image, we go through the convolution neural network, and then we use the features extracted for classification. Here is a part of the whole image. And here you can see that the nucleus part are whitened, okay, because the nucleus feature is here. And the rest of the structural, structure of the different cell, that is, that is retained here. And that also is used for feature extraction. So when you use the both, so this is the new part which we added, okay? And of course, we told that instead of just convolution neural network, if you use the dense neural network, then you get a better result, okay? So when you add this feature with the original nucleus feature, then we can get much better results. So I go to the result part. This is the voting mechanism where in a specific biopsy image, if 2 nucleus is classified as grade 0, only 4 as grade 1, only 2 as grade, only 1 as grade 2, 3 as grade, 34 as grade 3, and 137 as grade 4. So you see, if you vote, then grade 4 is the highest, which is classified. So the whole biopsy image we grade as grade 4, because grade 4, the number of grade 4 nucleus classified as grade 4 is much more compared to others. Of course, because grade 3 and grade 4 are very near, there are a few which are classified as grade 3, but you can see, I mean, overwhelmingly grade 4 is more, and the voting process is not confusing. I mean, it is always gives a very straightforward voting. Okay, and to emphasize that by using the global feature, we can get much better result. Here is a experiment 1 where we don't use the global feature, and the average classification accuracy is 94%. Whereas if we use the global feature, I mean, structure of the different cells, then we get 99%. So this is the amount of, I mean, improvement from 94% to 99%, okay? And yeah, this is, yeah, and I think I should go there. So out of 296 biopsy images, when you classify using our method, then you see only 1 is misclassified, okay? This is the classification of biopsy image, which is important because finally we have the biopsy image and you have to classify them. And out of 296, only 1, I mean, misclassification, accuracy is very high. And this is comparison with many other works, which some of them are quite recent. And you can see that we did 5+ classification. Sometimes the classification is only whether it's cancer or not. So 0, 1, they put in non-cancer, and 3, 4, they put in cancer. And sometimes it is 3-class classification when they say that 0 is healthy, 1, 2 is early stage, and 3, 4 is late stage. Of course, this classification number is less means higher accuracy could be achieved. We classified from 0 to 4, all the 5 levels, and still in every cases, our accuracy is much better compared to the previous ones, okay? And this is the conclusion where I wrote something about how we can convince a doctor and things like that, but I'm not going into the detail because my time is up, and thank you very much for your kind attention. I'll be very happy to get any question if you have.
Thank you for your nice talk, actually, and it is interesting. So some questions should come, I think.
So if you have any question regarding deep neural network or any question regarding object detection problem, you can ask. Actually, I don't have the slide, but we take a box around the boundary. And when we take the box, we take a little larger size so that everything is included. Now, how I mean, the exact algorithm I haven't explained here, but as you said, if it is a irregular boundary, then in some direction it is more, some direction it is less, like that. So we covered by using a box which includes the whole thing. Not really like that. We do something like that. Actually, we take the center of the point, and then we take the longest distance, and then we add some 10 or something. It's a very heuristic method, but it worked. But I don't have the slide with pictures. I could have explained in a better way.
So any other question?
Yes, please.
Please.
Sir, I have an out of track question.
Go on, please.
Sir, actually, I'm trying to work with multi-objective optimization and going to find a new geometry-based solution. But I'm facing a particular problem of I'm representing the multidimensional thing into the 2-dimensional picture. So
For that, I mean, there are many methods, and data visualization is a separate subject. So data visualization means, of course, when you visualize, you can at most, I mean, render in 3 dimension, but basically 2 dimension. Okay. But most of the data may be 100 dimension, 200 dimension. So
Then
how
is the problem, sir.
how to represent that? One simplest way is to do PCA and take the first 2 and then, I mean, project your data. For example, if I go to my slides, this one, actually, we took 64 dimension. When we extracted the features from the image using convolution neural network, we took 64 dimension, but then we project to 2 dimension using pincer component analysis. Pincer component analysis is the most general and efficient way of doing that. But there are other, like TNN is one method where they use convolution neural network for projection.
Sir, how did you take 64 dimensions? Because
No,
generally-
I mean, if you see the convolution neural network is nothing but a series of filters. Okay. Now, by increasing the number of filters, you can increase the number of features. Okay. And they're trained by using Boltzmann machine. If you increase the number of layers, actually every layer represents a set of filters, and they extract. Filter means they extract a particular set of features. And what do we do? That we combine them and combine them. So these are more abstraction of the previous features. Okay. And depending on the number of filters you are using, the number of features extracted will be more. If you study convolution, you will easily understand. Okay. Here we extracted 64. So 64 is the dimension of this image. Okay.
Thank you, sir.
So someone asking question, yes.
Yes, please. Exactly. I understand your question. For there are 2 types of diagnosis. Okay, one is intervention, one is non-intervention. Non-intervention is definitely better. You go and lie down and take MRI or CT scan, and from that image you get. But because CT scan or MRI, if you have seen, it's very, it doesn't give a conclusive, definite decision. Then if from MRI or CT scan image, the doctor sees that there is a possibility, they go for biopsy. So biopsy, we have to put a pin, extract a sample of the cell, then you have to cultivate the sample, and then you get the biopsy image. Yeah. So biopsy image is intervention, and you have to stay in the hospital half a day or sometime 1 day. Yeah. So this is biopsy image, but biopsy image are more conclusive, and that's why, yeah.
Good afternoon, sir. So this said.
Oh, quite far.
Yeah. So I have a question. As
Yeah.
I understand from your discussion that it is difficult to convince the doctors if the features that are extracted are not visualized well. So what are the steps which are being taken?
This is a very good question and very difficult question, but I will try to explain. Okay. As I have just told that here 64 features are extracted. Okay. Features means nothing but some values. Okay. And you combine, actually all the features the doctors see, the doctors don't see 64 features. They see 8 or 9 features, which are geometric features like sphericity, whether it's very good spherical or it's not very good spherical, or the boundaries are lobulated. Lobulated mean like this, or boundaries are smooth, things like that. Okay. So, but all those features are sort of hidden in those 64 features. Okay. Now, if you can combine, it's a combinatorial problem. some of these 64 features, when combined properly, will show some of the features which doctors look for. Okay. Now to search that is a combinatorial optimization problem, it's a hard problem. I mean NP problem. That we need to solve. Okay. If we can solve that, then we can show that, okay, you see, this is your lobulation degree. This is your sphericity degree.
Right.
And then
Then the doctors will be convinced. Otherwise,
then they will be convinced. But that is a NP-hard problem.
right.
And we need to do, I mean, I have some idea, but this paper doesn't include that.
Okay, thank you, sir.
Yes.
Regarding the patch image, sir, I wanted to know if it was an issue of overfitting in the.
Yes. I mean, actually, sometime you are talking about overtraining and
Sir,
or
specifically, sir, did you randomize the patch image, like rotate it, or
yeah. I mean, I tell you, actually, if your data is not balanced, and usually for medical data, they are not balanced. It's very easy to get a healthy data sample, but it's very difficult to get a level 4, grade 4 cancer data. Okay, so this is a data is not balanced. Okay, but we need to increase the number of data where the data is scarce. How to increase that? That is by changing, I mean, orientation, by changing size and things like that. And that is data augmentation. Here, data is more or less balanced, so we do not need any data augmentation. Okay. But if your data is not balanced, then you have to do that. In another work where we did on lung cancer, and that data was very much imbalanced, so we have to do some to increase the cancer. Actually, in lung cancer, they call nodules. We have to increase the number of cancerous nodules by augmentation. Yeah. But there's another issue, which is overtraining of the convolution neural network. Because there is no question, I'm not going to, address that. And probably the program chair is already angry with me.
There are 64 features you mentioned that one. Are they equal importance or different importance?
64 pictures? No, 64 features. Yeah. We really don't know. But as you asked me, I'll answer. We can run a feature selection after that. So I don't know, probably someone will talk about feature selection. So out of the 64 features, this is the classifier part. So we can run a feature selection here, and then we can see that some of the features, 64 features, are not so important. But we didn't did that.
You said that for doctors are showing only 8 features.
But those 8 features are actually some combination of these 64 features. And those combinations may be overlapping too. Yeah, but that is the weightage about these 64 features. But that doesn't represent the features that the doctors are looking for. Those are again some different combination of those features. Okay, and sometimes feature decreasing the feature of the number of features, sometimes it improves the result, sometimes it doesn't improve the result. So those are again some different issues.
Yes.
No, it's all arbitrary. Arbitrary.
Yes,
but it has been actually it is mathematically proven, and it has been shown by many experiments that doesn't matter if it is not too small or too big. But what is too small and too big? So usually 64 is okay. And another thing is that nowadays, most of the deep neural network or convolution neural network, you get the pre-trained one, already trained. And then they're trained by some different data. And then you train with your own data. If you get a pretend data, then you don't need to change the numbers. Why? Because you cannot. And why it is good to get a pretend network? Because your training will be much faster. In fact, sometimes one epoch of training may take several hours. Okay. But if it is done by someone else, for example, I have a GPU 1080 machine, which is not very strong, but Google has a very big machine and they pretend. Usually Google does. Then you get that pretend network and then training with your data, you can do the training within maybe 1 day. But otherwise you may need 1 week. So we don't really change much of the configuration is retained as it is. Any other questions?
So this is an interesting talk. Naturally, everybody will be interested. So
Yeah.
time is short, so better you can talk
Yeah,
with him outside. Yes.
if you Google my name, Google Gautam, it will come probably first. Or Google Gautam Japan, it will come first. You get all my information, all my pointers. Please mail me. I'll be happy to answer you. And before Shamarjit fire, I mean, he's very angry. I leave. Huh? Pointer taken. Shamarjit,
Thank
sorry.
you.
Sir, please go ahead. Now, as a mark of appreciation of our speaker's presentation, I would request the session chair to offer him memento. Yeah.
He'll also come.
Thanks, sir. And now, Professor Shandip Chatterjee will felicitate the session chair. Sir. Yes. Thanks. Yeah.
I started with that in the hospital. We have tomorrow evening, we have a classical music conference.
Thank you, Speaker and Session Chair. We come to the end of this session, and we would start the next session right away. Just give us a little time. Start the next session. Okay, so I request Professor Mihir Chakraborty to take the stage. He's the session chair. We start the second session, and we welcome on the dais Professor Mihir Chakraborty, who is currently a visiting professor at the School of Cognitive Science, Jadavpur University, Kolkata. He was a professor at the Department of Pure Mathematics, University of Calcutta, Kolkata, India. He has been a visiting professor researcher at many reputed universities worldwide. Notable among them are IRIT University, Paul Sabatier, Toulouse, France, University of Helsinki, Finland, University of Paris 13, France, Institute of Mathematical Sciences, Chennai, Center for Soft Computing Research, ISI, Kolkata, and University of Warsaw, Poland. Professor Chakraborty's research interests are in non-standards logic, rough set theory, fuzzy set theory, topology, functional analysis and philosophy of mathematics. He is one of the founding members of ALI, Association for Logic in India. He has published more than 150 papers in journals, book chapters, conference proceedings, and has edited several volumes. Along with Professor P. Pagliani, he has co-authored a book titled Geometry of Approximations, also a distinguished writer in Bengali of articles on mathematics and various other subjects. And I have the pleasure to state that I have known him for at least 30 years, early 1990s. I was a student and he was a senior professor at that time. And it's a pleasure to hand over the stage to him. He will be chairing this session. So.
Thank you very much. We have two very distinguished speakers in this session, Professor Roman Slowinski and Professor Andrzej Skowron, both from Poland. First is Roman. Both of them, incidentally, are very close friends of mine. So, welcome, Roman. Do you hear me?
Yes, I'm hearing you.
Good. Professor Roman Slowinski is a professor and founding chair of the Laboratory of Intelligent Decision Support System at Poznan University of Technology, and a professor in the Systems Research Institute of Polish Academy of Sciences. As a full member of the Polish Academy of Sciences, he has been elected its vice president for the term 2019 to 2022. He is also a member of Academia Europea and fellow IEEE, IRSS, Informs, etc., etc. So there are lots of things to say about Roman, but you will get it if you click in the internet. And so, Roman, I am not really taking much of your time speaking.
Yes.
So better start your talk. Thank you.
Thank you. Thank you very much. Good morning from snowy Poland. Thank you very much, Mihir, for your generous introduction. And I wish to thank also Professor Samarjit Kaur, the program chair, for having this initiative of inviting me to this very important meeting of the Operational Research Society of India. This is the 55th annual convention, and I am particularly pleased that it is also a tribute to Professor Mahalanobis, the first president of this society, because this year we are celebrating his 130th anniversary. The talk that I would like to make today is about a typical topic of operational research. I will share with you my slides. I hope you can see them. The topic is about preference learning by robust ordinal regression for multiple criteria decision aiding. This topic is very typical for the current trend of operational research that is converging with artificial intelligence. You will see that there are links between the methodology of multiple criteria decision aiding and artificial intelligence through preference learning. The plan of my talk includes the parts which are in black characters. The topic is much wider, so I am not able to present you everything during my half an hour talk. However, I will start with introduction to the challenge, and I will then present the methodology, which is called robust ordinal regression. And this robust ordinal regression will be presented for three kinds of preference models, because preference models will be crucial for this methodology of decision aiding. And one is a value function, or otherwise utility function. Second is outranking relation. And third is a decision rule preference model. And this model will be based on rough set concept. I will present two exemplary applications and I will come to conclusions then. So what is the challenge? The challenge is, of course, a decision problem, which can be defined in a very general way. To have a decision problem, we have to have an objective or objectives to be attained, and there should be many alternative ways to attain these objectives, and they constitute a set of possible actions. These actions may be called also alternatives, solutions, objects, patients, acts, etc. But in general, we will call them actions. And the questions with respect to this set of actions may be the following. How to choose the best action? What is the best action? How to classify actions into some predefined decision classes? And finally, how to order actions from the best to the worst? So the choice problem is graphically presented here. We are interested in the subset of best objects, of best actions, and we discard the others without taking care of their order. Classification is assignment of actions to predefined decision classes, which may be ordered from the best to the worst. And ranking is construction of the ranking of the preference ranking of the actions from the best to the worst. However, this ranking, because of some lack of information or some conflicting information, may be not complete. Then, facing the problems of choice, classification, and ranking, we have to take into account that the actions themselves may be evaluated on multiple attributes, that the evaluations of the actions are vector evaluations and non-single values. Why? This may come from three sources. The first one is the existence of multiple decision makers, voters or participants of group decisions. They may have different points of view, they may have different value system, so they may value the actions in a different way. From this, a vector of evaluations come out. Second source are multiple criteria. So even if you have a single decision maker, this decision maker may, upon reflection, come to conclusion that the actions are evaluated from multiple points of view as well. Yes, that there may be some criteria which should be maximized, some others should be minimized, and those criteria are in conflict. If you improve one, you deteriorate the other. So also the actions taking into account this point of view are evaluated by vectors. And finally, there may be more than one possible states of the world. And the consequences of the actions may be probabilistic. For example, in decision under risk and uncertainty, you may have many scenarios and consequences will vary, consequences of actions will vary depending on those scenarios. So again, actions are evaluated by vectors of evaluations. So those three sources of vector evaluations of actions of elements of set A gave birth to three big disciplines that developed after the World War II as almost independent. However, they have something in common. the presence of multiple decision makers of group decision gave birth to social choice theory. The consideration of multiple criteria gave birth to multiple criteria decision aiding or decision making methodology. And finally, we have also decision under risk and uncertainty. So elements of set A may have different names in those three big fields, candidates, actions, acts, and dimensions in evaluation space are voters, criteria, probabilities of an outcomes, gains or losses. Yeah. However, one information that joins these three big subfields is dominance relation in this set of actions, candidates, acts. This is the only objective information. To convince you about, I am giving here a very simple example for a social choice, multi-criteria decision aiding, and decision under risk and uncertainty. In the first case, we have 2 voters and 3 candidates, and the candidates are ranked by voters in a different way. So voter 1, B is the best, C is the second, A is the third, and voter 2 in a different way. So we can represent this situation on a plane, coding the positions of the candidates on this plane. For example, A is the third for voter 1 and first for voter 2. And what can we conclude from this easy picture? We can conclude that C as candidate is dominated by B, because B is on a better position by both voters. However, B and A are non-comparable. So the dominance relation in the set of 3 candidates shows that B and A are the best to be considered, however non-comparable, and C is dominated and can be discarded. In decision under risk, in multi-criteria decision aiding, we have a similar situation, even the same number coding, because action C is also dominated by action B on time and cost, and A and B are non-comparable. As to decision under risk and uncertainty, we have, in this case, stochastic dominance, because we are speaking about probabilities. So we have 2 possible gains. The second gain is higher than the first, and probability of attaining these gains, of course, should be maximized. So we invert the direction of preference, and we see again that Act C is dominated by B because it is promising a higher gain 1 and gain 2 in both probabilities. So C can be discarded, but again, A and B are non-comparable. So what is the conclusion from this introduction? The conclusion is that although dominance relation is objective and common for all these 3 subfields of multidimensional decision problems, it is too poor because it leaves many actions non-comparable. So what we can do in order to make them more comparable and solve the problems of choice ranking and classification? To enrich the dominance relation, we will use preference information. And this preference information is a subjective information representing the value system of the decision maker or decision makers, and should be elicited from them. The preference information is then an input to learning or building a preference model that aggregates the vector evaluations of actions. And then the preference model induces a preference relation in the set of actions, which is richer than the dominance relation. This makes that the elements of A become more comparable. Then, when we have this preference relation and set of actions, we have to exploit them in order to work out a recommendation in terms of choice, classification, or ranking. So you see that in the decision aiding process, we have three characteristic stages: preference information elicitation, and based on this, preference model learning, and third, exploitation of the preference relations that comes from this model in order to give a recommendation. And the many methods that were proposed in operation research to solve these multidimensional decision problems are differing exactly at these three stages: by kind of preference information, by kind of preference model, and by the way of exploitation. In my talk, I will concentrate on multiple criteria ranking. However, I would underline that the methodology is the same for all these three subfields with some details, of course. What aggregation of multiple dimensions in case of multiple criteria decision aiding of criteria do we have? So what preference models? So taking historically, we have first a functional model, which comes from multiple attribute utility theory. The multiple attribute utility theory is proposing to use a synthetic value function, which is aggregating evaluations on multiple criteria to a single score, to a real value. And then this value permits to order actions from the best to the worst, to choose the best, and also if you give some thresholds on this value function, to classify. The value function may be very similar, very simple, like here, this weighted sum. However, it is simple mathematically, but to give responsible answers about the weights is not so easy for decision makers. It may be more a general additive function composed of marginal value functions, which do not need to be linear. Or in case of interacting criteria, we may have the integrals of Choquet for cardinal scales of criteria and Sugeno for ordinal scales of criteria. The second, historically also kind of aggregation model is a binary relation model, which is called outranking relation. Outranking relation has been proposed by so-called European School of Decision Aiding, and its principal figure was Bernard Roy, who passed away 2 years ago. And Bernard proposed outranking methods called ELECTRE methods, which are supposing that we have an outranking relation S, grouping indifference, weak preference, and strict preference. And this relation is true for actions A and B if A is at least as good as B. However, as we will see later, this relation and these methods permit to handle also incomparability that multiple attribute utility theory does not permit. And then we have the most recent aggregation model, which is through decision rules, and decision rules which are monotonic, which engage a subset of criteria in their condition part, and conclusion, which is either for classification or for ranking. Why the syntax of rule is different for classification and for choice and ranking. In classification, a decision about assignment of an action to a class is based on some standard of classes, which are created by those thresholds which are induced from data, threshold R. In case of classification and ranking, we have to establish pairwise relations between actions, because a position of an action in the ranking depends on the quality of its competitors. So this is why we engage pairs of actions in the condition part and some intensity of preference for cardinal criteria on selected criteria in the condition part. And when this idea of modeling preferences with decision rules has been proposed by my doctoral student Salvatore Greco and myself, and it was based on the concept of dominance-based rough set, there was a question by the referees how this model compares to the others. Comparing models of aggregation is not easy. It cannot be done by the comparison of the end results of application of these models, but rather at the axiomatic level. And we did such analysis on axiomatic level to see which of these models is requiring the weakest assumptions to build a preferences to build a preference model of decision makers. It appeared that the most general model is the model of decision rules, and others exist if and only if the decision rule model is able to represent the preferences, which is a very interesting and strong result. Moreover, rules are representing preferences in an explanatory way. Those by utility function or outranking relation are rather like black boxes. However, decision rules explain the scenarios of cause and effect and relations between the holistic judgment and elementary conditions on particular selected criteria. I will present to you the robust ordinal regression using a simple example of ranking of countries with respect to digital economy. The data are taken from Economist Intelligence Unit in 2010. So here in this example, we have 17 countries that are evaluated on 6 criteria, which are evaluating the quality of information and technology infrastructure. And we have 17 vectors corresponding to evaluations of those 17 countries. And the challenge is to make the ranking of these countries, which is the most adapted to digital economy in the sense of the ranking from the best to the worst. So now we have to face the question, how shall we elicit the preference information to build the preference model? Should we ask the parameters of a predefined preference model directly from the decision maker, or maybe should we observe her actions so as to build a preference model? So the first way is so-called direct way. Direct way is through elicitation of numerical values of model parameters by decision makers, and it demands a lot of cognitive effort. Yes, already in 1967, Peter Fishburne, a great name of decision analysis, he reported 24 methods of estimating additive utilities. So additive utilities like those on the left need to elicit either the weights or the shapes of marginal value functions. So there is no way which would be the best. You see in 67, there were already 24. And in case of outranking relations, there are even more parameters to be defined by decision maker, and decision maker who is not an expert in decision aiding in operation to research is rather not able to give those parameters with full responsibility. So rather indirect elicitation of preferences should be considered through holistic judgments. What are holistic judgments? Holistic judgments are just decision examples that do not decompose the evaluations into particular criteria, but say in a holistic way which one is the best, or what is the comparison, holistic comparison between pairs of actions. Decision aiding based on decision examples is today gaining importance, and this is for 3 reasons at least. Decision examples are relatively easy preference information. Second, decisions can be observed without active participation of the decision maker. And we are today witnessing this phenomenon because all our actions in internet, for example, are recorded by some special applications. And based on our behavior, which is also a set of holistic judgments, there is created our preference model, and then we are getting, for example, the advertisement which is adopted to our interests. Also, psychologists confirm that decision makers are more confident when exercising the decision rather than explaining them. And the names of John March or Paul Slovic are here to be quoted. Also in economy, Paul Samuelson, before the World War II, he wrote about revealed preference theory, which is a method for analyzing choices made by individuals. And finally, in artificial intelligence and machine learning, we have today the slogan of learning from examples, of knowledge discovery. And so this is just also learning from holistic judgments. So in conclusions, people working on multiple criteria decision aiding understood a few decades ago that the indirect elicitation of preferences is more user-friendly. And this is why we are proposing this approach also here. What are examples of indirect preference information? These may be pairwise comparisons between alternatives. Alternatives are then represented by vectors of evaluations. And then the decision maker will say, oh, for example, this vector is for me more attractive than this one. But if a decision maker would not like to enter into precise values of alternatives of actions on particular criteria, then it is also possible that they are comparing holistically, like here. I prefer this car to this car. And behind the screen, there are some cardinal ordinal features characterizing these actions. Or I prefer this book than this book to learn about preference learning. Yes. For classification, there are assignments of typical actions to class of medium, to class of good. There may be also an expression of intensity of preference. A is preferred to Z more than C is preferred to K, not necessarily on a cardinal scale, like some methods are forcing to do. Yes, because this information A is preferred to B 3 times more than C is preferred to K is really unrealistically very difficult. And some other information, for example, action F should be among 5% of the best ones. So these are examples of holistic preference information. And the first method that realize this paradigm of ordinal regression, because this is a backward calculation of a model based on holistic preference information. And if this model reconstructs this holistic preference information, we can claim that this is a preference model of the decision maker, and we can use it on the whole set of the actions. So the paradigm says that there is a subset of actions which may be relatively well known to the decision maker. These are so-called reference actions. Those reference actions may be pairwise compared by the decision maker, who is expressing in this way her preference information. And then the analysts, so we are computing a preference model which is, for example, an additive model composed of marginal value functions, which is compatible. This means reconstructs the pairwise comparisons of the decision maker. And if we are successful, then we can apply this on the whole set A and make the evaluation of all the actions using this value function, and then rank or classify or choose the best. This method has been proposed in '82, so already 40 years ago, by my colleagues Jacques Lagrèze and Ciscos, and published in European Journal of Operational Research. So this backward step of calculation is easy because calculating even piecewise linear or just monotonic marginal value functions can be realized using linear programming. So linear programming is a very efficient method. So it is very quickly calculating a compatible value function. So in this example of 17 countries, if we would dispose of 3 pairwise comparisons like here by the decision maker, then the marginal value functions from 1 to 6 compatible with this pairwise comparison would make the ranking of the 17 countries in the following way. First would be Sweden, then Netherlands, etc. However, there is the problem of non-univoqueness of the solution. There may be an alternative value function which is also compatible with pairwise comparison, which is reconstructing this pairwise comparison, but it is ordering the actions in a slightly different way. Still keeps Sweden before Denmark and UK before Malta, etc. However, now Netherlands, according to this value function, is the best. So what to do? For this, we proposed robust ordinal regression. And the paradigm does not change so much. However, in this step, we are considering all instances of preference models compatible with preference information. And then we are applying all compatible instances, even if there is an infinity of such compatible instances on the set of actions A. And then we are getting relations which are either possible for any pair of actions or necessary. A necessary relation holds when for all compatible value functions, value of X is not less than value of Y. And possible relation holds when value of X is as high as value of Y for at least one compatible value function. And the properties are very intuitive of those necessary and possible preference relations. To explain you graphically how it works, I am giving here a small example. So here we have this input preference information, pairwise comparisons. Through linear programming, we are able to assess the range of variation of marginal value functions which are compatible in total with those pairwise comparisons. And here we have a necessary preference relation, which is, of course, reproducing those pairwise comparisons, but at the same time, some actions also enter into necessary preference relation. What happens if I add a new pairwise comparison in the second iteration of the dialogue with the decision maker? So when I add this information, so the area of compatible value function is decreasing. It is constrained, and more actions are entering into necessary preference relation. So we see that with new pairwise comparison, the necessary preference relation is enriched. When we start from 0, no preference information, then necessary preference relation is a dominance relation. And then step by step, it is more, it is richer than the dominance relation until they can give a linear ranking, of course, but we do not need to come to the end. So in our case, so this is the necessary preference relation for those 3 pairs of comparisons. So you see that some countries are non-comparable, but some are comparable using the necessary relation. So you see that the robust ordinal regression works in a loop. with incremental elicitation of preferences. And this is so-called constructive learning. It is very similar to preference learning in machine learning. We compared this approach with preference learning from stochastic point of view in this machine learning issue. Why it is robust? Because it takes into account partial preference information. Only few pairwise comparisons are necessary to make an estimation of the set of compatible preference models. So here I am giving you the proof that the calculations are through linear programming, even if there is no constraint on linear character or piecewise linear character of marginal value functions. They need only to be monotonic. And so I will not enter into details. All calculations of necessary and possible preference relations are through linear programming. And also, we may have additional preference information. For example, we proposed a new method based on the UTA GMS, which is called GRIP, and that permits also to handle intensities of preference in the sense that, for example, X is preferred to Y at least as much as W is preferred to Z on all criteria or on a particular criteria. And then we also have linear programming. And in case we are not able to represent the preferences provided by the decision maker, we can also identify and eliminate those troublesome pieces of preference information through 0-1 linear programming, easily solved. Continue with not completely compatible set of value functions, or augment the complexity of the value function. And we also did it in our past. We, for example, substituted additive value function with Choquet integral or augmented additive value functions taking into account interactions between criteria. So I will skip representative instance and extreme ranking analysis, and I will come to outranking relation preference model. So outranking relation preference model was proposed because value function does not permit to handle incomparability. And also the transitivity of indifference is sometimes problematic if the actions are different by a very small margin. So we may come by transitivity to a paradox of indifference of very different actions. So this is why outranking methods have been proposed. The most well-known Electr methods and Prometee method, MAPAC, Pragma, and several others. So the criteria in outranking approach are equipped with thresholds. The indifference threshold, preference threshold, and we can see that if we construct the outranking relation for all ordered pair of actions, and we may have indifference, large preference, or incomparability, which cannot be modeled using the value functions. And the construction of the outranking relation is through so-called concordance and discordance test. The concordance test is checking if the coalition of criteria which are concordant with the hypothesis that A is at least as good as B is strong enough. And for this, we have indicator CI from each criterion and weights. However, these are voting weights. These are not substitution rates for all criteria. And from this, we are inferring the degree of concordance in the coalition of criteria concordant with the hypothesis A outranks B. And then we have discordant test to check if among criteria discordant with the hypothesis A outranks B, there is a strong opposition. A strong opposition, it means that the advantage of B over A would be over some veto threshold. Yes, so this is one of rare methods that takes into account negative arguments of similarity of preference. And then finally, we are getting a relation of outranking. The outranking is true if the concordance is above the threshold of, say, for example, 75%, and there is no criterion strongly opposed making veto to the hypothesis. So we have, in fact, a graph of the outranking relation. And from this graph, we can extract the kernel to choose the best actions or to make the net flow score of each action and to get the ranking. So in order to make the robust ordinal regression, we are folding this weighted sum into a single function that is unknown. And then we allow that decision makers are giving the holistic preference information on reference actions. For example, like this, that action A is outranking B, but in another case, action C is not outranking action D. And there is some range of indifference threshold and some range of preference threshold. So this is the only preference information. The decision maker does not need to propose all those precise parameters like weights, like thresholds of indifference, preference, and veto. And then in the robust ordinal regression, we have again monotonic functions for the concordance functions. This is obtained through 0-1 linear programming, and possible and necessary relations are also obtained through optimization. So finally, we are getting necessary and possible outranking relation. And having necessary relation and the inverse necessary relation, we are evaluating the position of each action, taking into account its positive relations and its negative relation. And the subtraction of positive and negative is giving the score, which is called net flow score of the action. So continuing our example, having such preference information, we are getting the necessary outranking relation like that. Augmenting the preference, we are getting more dense outranking relation. And then through the kernel, we are finding the most interesting D and F countries, or the ranking of countries from the best to the worst. And finally, decision rules. So decision rules have this syntax that I already characterized in my introductory slides, so I will not repeat this again. I would like to mention that they are induced from holistic judgments, from decision examples, after structuring of this information using dominance-based rough set concept. The dominance-based rough set concept is an extension of the Pawlak's indiscernibility-based rough set concept, because it substitutes indiscernibility relation by dominance relation. Again, this objective information and multi-criteria decision aiding, and we have to take into account possible inconsistencies, not with indiscernibility, but with the dominance relation. So this is why we are approximating the classes which are preference ordered using dominance cones and not granules, which are closed sets. So I will finish with this small example. Let's say that we have 8 solutions characterized by 2 functions which are to be minimized. And the decision maker is asked to provide the holistic judgments, which of those solutions is good and which is bad. Let's say that those red are bad and those green are good. So then the lower and upper approximation of good and bad would look like that. And then you would see that in between, so solutions 8 and 7 are inconsistent, because 8 is considered good. However, it has worse evaluations on F2 and F1 than X7. So those are in the boundary of good and bad. And now, after such structuring, we can induce rules. And look, that rules are quite simple and they are supported by our examples. These are certain rules which are induced from lower approximation, and these are possible rules which are induced from data structure using upper approximations. Decision problems that were handled with this decision rule model were numerous. We applied them in hospital. I have no time to speak about, even to characterize the preferences of the jury of violin makers competition in Poznań. I will finish my talk with conclusions that robust ordinal regression is nowadays a constructive way of learning decision makers' preferences, that decision makers' preferences are still to be handled in operational research problems or decision problems. This robust ordinal regression has been adapted to discrete choice, but also to multi-objective optimization. Following our master Bernard Drouin, we may say that robust ordinal regression is in line with his advice of how to approach decision aiding. So thank you very much for your attention. I have 3 minutes for questions, so I will devote this to your voices. Thank you very much for your attention. I cannot hear you. Unfortunately, I cannot hear you. Can you hear me? Oh.
Can you hear me, sir?
Yes, yes, now yes, now yes.
So maybe you can come to this mic. Yes. Yeah, just a moment. Yes.
But my question is now, did you hear me before?
Yeah. That was okay. Quite all right.
Okay.
So I will take a few questions, quick questions. So please raise your hand. Yes, please. Again, there will be a problem, I think. I think you have to come here.
First of all, this is also a preference relation because I cannot speak from the dais. I have to come here. So this is a preference relation. So idea is that preference relation can be probabilistic or possibilistic.
Yes, sure, of course, yes. We consider also hybridization with fuzzy sets to express degrees of preference intensity. And this is also very useful in the case of the presence of some other imperfectness of data. Because Dubois and Prad at some time when we was discussing about the advantage of rough sets over fuzzy sets and vice versa, they stopped the discussion. This was early 90s, and they said there are different imperfectness of information, and there are imprecision, uncertainty, and also ambiguity, and those all kinds of uncertainty of imperfectness can be handled together, and this is enriching our models. Sure.
Thank you, sir.
Thank you very much.
Yes, maybe another 1 or 2 questions.
Anyone? You can use this
Anyone?
microphone. No?
Yeah, here, please. Okay. Do you see all of us? Do you see the
Yeah.
audience?
No, but I see you and, oh yes, now I see.
Yeah, okay.
Yeah, good afternoon, sir.
Good
I have got a
afternoon.
question. Can you hear me, sir?
Yes, yes.
Okay. So, sir, as you said, preference models are better than the dominance model, right?
The preference model
Preference
are,
models are richer than dominance model.
yes, yes, yes.
Yeah. But in that case, the result may be inconsistent if the decision is based on decision maker and if it is based on indirect implicitation of the. So, are you getting my question? In case if we go by
how it
preference
is,
model,
yes, but
Not
I
clear,
wonder how
not
it would, how
so
it
if
would
we
be
go
possible.
by the preference model,
Yes.
in that case, the decision can be taken based on the decision maker, or it can be based on indirect implicitation, holistic approach.
Yes, yes. In holistic approach, the preferences are richer than dominance relation, because I show that some actions are non-comparable by dominance relation.
Right.
But the decision maker is saying, I prefer this one, even if they are non-comparable. So we wonder, is there a model that shows that this decision maker will prefer in such pairwise comparison of non-comparable objects by dominance, that one? And if we are able to answer, we have a model which will then be applied to different pairs. And we'll discover, okay, so according to previous preferences, this one of non-comparable is better. So this is the idea of first looking at the holistic preference information from the decision maker and building a mathematical model which will reconstruct this choice, this preference information, and will claim that this model is representing the value system of this decision maker.
Okay.
This is the idea.
Okay. Thank you, sir.
Thank you for your question.
Yes. Okay, it's all right. Okay, all right. Roman, I think we have to unfortunately stop here because we have to pass on to Andre.
Absolutely, yes. I will not take the time of my friend.
Very much. I thank you very much for virtually coming to Kolkata. Actually, we had been trying to bring him here. Samarjit was trying for several times, but this is how we have ultimately got Roman in Kolkata.
Thank you very much.
Maybe next time
I hope that
a better way. Okay, so
thank you very much.
Let us give a big hand to the speaker.
Thank you very much. Thank you.
And thank you, Roman. Okay. So I use this mic. I would like to. It's okay now? Okay. So our next speaker is Andre Skovron, Professor Andre Skovron. He is a very well-known figure in the RUFSET community, RUFSET area. He's a fellow of International RUFSET Society, member of East European Academy of Sciences, received the PhD and DSc habilitation, etc. from Warsaw, University of Warsaw. He received the scientific title of professor. He is a full professor in the Systems Research Institute, Polish Academy of Sciences, and he's at present emeritus professor in the Faculty of Mathematics and Computer Science and Mechanics at the University of Warsaw. Again, I should simply say that is a very well-known figure, and you will get all the information about Andre Skovron from the Google. So Andre, do you hear me?
Yes, I can hear you.
Andre?
Yes, so I will share my screen. Yes.
Okay. Good. So welcome to Kolkata. He has visited us, I mean, in Kolkata several times before, maybe 2 or 3 times, as far as I remember. I now invite Andres Cobron to present his talk.
Yes, thank you very much, Mihir, for your kind introduction. First of all, I would like to thank you, Professor Samarjit Kaur, for the invitation. And also I would like to thank my colleagues and especially to one representative of India, Professor Shoma Dutta, who survived in a long discussions with me about this interactive granular computing and helping me really to better understand what I have in mind. I hope that I will be able to present some intuition behind this idea. So maybe you are familiar with granular computing, and I will try to explain what are this interactive granular computing and how it is related to intelligent systems, especially to intelligent systems which are dealing with complex phenomena. So first of all, I would like to tell you about the main goal of such intelligent systems, which I would like to discuss, and a very short presentation about the current status of the main goal realizations from perspective of rough sets and granular computing. And the main topic I would like to discuss are motivations for development of a new computing models for intelligence systems which are based on such computing model, which we call interactive granular computing. Some preliminaries related to this model and how I see the foundations of such information intelligent systems based on this model, and a short summary. So what is this main goal? You can imagine that these intelligent systems are working to discover of a kind of the complex games together with their evolutions in the context of interacting abstract and physical worlds. This is very important that we have these two sides, this abstract world and the physical world, which is outside of this abstract world. So in this case, which you can see in this picture, is similar to this, what you can find maybe in reinforcement learning, that we have some concepts which are represented here by these colors, and also they are labeled by actions or plans which are triggered as soon as these concepts are satisfactory to a degree. The problem is that these concepts are complex and vague, and these concepts is necessary to discover from the data we are perceiving about the reality. Moreover, over the time, when we observe the situation, for example, on the market or the financial market or whatever, in this complex situation, these concepts or vague concepts are changing. So it is necessary to be continuously ready for evolution of these models. So when we deal with such a decision problems, we have a lot of sources of informations. Some of them are like business units, some are general knowledge bases. We have the domain experts, and here we have this, what is becoming now very popular, human in the loop or human-centered AI discussion. And we have also literature, we have pools of sensors and robots, and so we have this different sources, and the systems should be able to interact with them and to take part in the dialogues. So this problem which I would like to discuss is related to the following issues. That we consider interactions of physical objects which are controlled and perceived by this what we call complex granules, or C granules in short. And the results of perceptions are encoded by information represented by data from which models, in particular these complex games, are constructed. So let us first discuss very shortly granular computing idea. This granular computing idea introduced by Professor Lotfi Zadeh. I am citing here a very important sentence included in one of his papers. He was saying that information granulation plays a key role in implementation of the strategy of divide and conquer in human problem solving. You can have a very formal specification, for example, or query asking if the situation on, if there is a high risk that situation on the financial market will change rapidly. And this is what Professor Zadeh is saying here, that humans are able to decompose this vague specification defined in the natural language into a hierarchy of levels and use this divide and conquer strategy on these expressions in natural language. We will go back to this. But for us at the moment, let's consider this granular computing defined in the following way, that we have some elementary granules which can be crisped, as this is shown in this picture, and this green part here. They can be a family of such neighborhood, or they of different sorts, and they can be also fuzzy. And what we have next, we have some operations on these granules, like aggregations operations, which, and this together is giving us a kind of the calculi of granules. In the case of rough sets, we can consider also approximations of granules, and the aggregation of granules are, at least in the very basic model, are definable granules. Let me say a few words about the main idea of rough sets. So when we see this table, which is presented in this on this slide, we have here some attributes, and we have some objects or situations which are perceived, and the result of the perceiving of the situations are the values of these attributes. So this situation is represented from the point of view of this, as we are saying, information system or data table, by the vector of values of these attributes. And the very basic relation is indiscernibility relation relative to a given set of attributes, and two objects are indiscernible if they have the same description, so this information about this object relative to the set of attributes is the same. So if we consider all objects with the same information, we have this neighborhood of X, or this very elementary granule. Of course, this relation was extended to not so strict, maybe to tolerance or similarity relation, but this is not so important for us now. And next, on the basis of this are defined approximations of a given set or concept in the universe of objects, and the lower approximations is the largest definable set, and definable sets are union of these indiscernibility classes included in the given set, and the upper approximations is smallest definable set containing this concept or a set. So, and difference between them is a boundary region. If this boundary region is empty, we have a crisp set, and a rough set is a situation when this boundary region relative to this given set of attributes is non-empty. So this story starts something like 40 years ago. So we now the rough sets have 40 years. And the first paper about the rough sets were published in '82. And next, this book by Professor Pawlak. Here is a picture with him presenting the rough sets during the very early conference in Banff in Canada. And now we have many thousands of papers which you can see in this database developed by our colleagues in Poland. So we have a lot of applications, also this which were mentioned by Professor Słowinski, but also by other colleagues, some patents in the US. And here is a long list of journals related to artificial intelligence, to very famous journal where these papers are published. Here is a screenshot from this database. So over the years, it was also possible to see that the rough sets are working very well in combination with other approaches, like for example, fuzzy sets, and also very many generalizations of rough sets were defined. Among them, this dominance rough set based approach discussed by Professor Słowinski, and also relationships of rough sets with other approaches like Dempster-Scheffer theory of evidence, and many others were developed. Let me mention one kind of application in which I was involved, which I am calling the rough set based ontology approximation. So this idea is was checked on several real-life projects, which I am presenting shortly here. On the screen, you can see the situation on the road, and you can observe, maybe this is the case when you have unmanned helicopter flying over the road making the video, and on the basis of this video is necessary to make the decision if the situation on the road is safe or not. So this complex concept, vague concept, is the safeness of the situation on the road. Here on this picture, this is emergency room where are admitted newborn children with respiratory failure. So they are staying in this emergency rooms for quite a long time with a lot of respiratory machines, medicine, and in this American Polish clinic in Krakow, they have collected a database of histories of such patients. And in discussion with them, they suggested that we can maybe predict if in a given situation there is a high risk of losing life by such a baby. Maybe at this moment we can maybe switch the lamp or make some noise or so to warn the doctor, or maybe we can help to predict a short-time therapy for such children. And another real-life project in which I was involved is related to automated trader. And here was another very interesting project related to sunspots classification on satellite images. This was the project in which was involved one of the member of our group, Professor Son Nguyen, and here was a project also very interesting about supporting the fire brigade officer during the real-life action. So in all these cases, we were looking for approximation of complex vague concepts. And the main idea was like this, that in the discussion with domain experts was possible to obtain a kind of the ontology of concepts. And the problem was with transferring this ontology of concepts to the language of understandable by the systems, starting maybe from the lowest level closest to the to approximation or easiest to be approximated by the system, and next in the bottom-up strategy, this classifiers for all these concepts were created. And this idea was quite successful in this project, in the number of projects, especially in this project which I mentioned here. So from the point of view of the more abstract idea, say from the mathematical point of view, the situation which we have here differs from this, what usually people in mathematical logic are doing. They are considering, for example, the language of formulas, the class of models, and satisfiability relation as given mathematical objects, and so they are playing with mathematical objects, deriving very interesting theorems. However, here we have the situation that that the structures are not given and they should be discovered from the data. Moreover, they should be discovered on different levels of this hierarchy. And this is the main difference between these approaches. But now we can ask what next? If we move from these problems to intelligent systems working on the basis of big data, continuously perceived interactions with complex phenomena in the physical world, we can ask the fundamental questions. If we have the relevant computing model supporting these issues in the case of cyber physical systems, Internet of Things, Wisdom Web, Society 5.0, and so on. And do we have the relevant computing model for developing intelligent systems which are dealing with complex phenomena? So you can find in the literature many partial proposals in many different domains, like multi-agent systems, machine learning, robotics, cognitive science, neuroscience, and so on and so on. But we need the relevant computing model foundations for for these intelligent systems dealing with complex phenomena. And such a model, this is important slide here, that we should develop tools supporting decision-making based on two things. First of all, construction of objects with abstract and physical layers on which computations are performed. And we need a reasoning mechanism about such computations. Let us remind what we understood by complex systems. There are such systems that the elements are difficult to separate. And this difficulty arises from the interactions between elements. Without interactions, elements can be separated, but when interactions are relevant, elements co-determine their future states. Thus, the future state an element cannot be determined in isolation, as it co-depends on the states of other elements. So this is this main idea I would like to show you. And now is a very important observation made by Frederick Brooks, who received the Turing Award for his work in software engineering. And he's saying something like this, that mathematics and physical sciences made great strides for 3 centuries by constructing simplified models of complex phenomena, deriving properties from the models and verifying these properties experimentally. And this worked because the complexities or details ignored in the models were not essential properties of the phenomena. However, it does not work when the complexities are the essence. So this is a kind of the situation that we should look for new kind of the modeling. So going to our very simple idea of red sets, when we started from this information system or data table, we should move to networks of information system which are dynamic and which are working in broader context, and to be able to represent interactions with the physical world, including humans. So this is like moving from this picture, which was isolated from the physical reality, to the picture where this is interacting continuously with the physical reality. And there is a kind of the reasoning, which we call judgment, supporting this discovery of computational building blocks, which we call complex granules over them for cognition. In the case of the systems, intelligent systems dealing with complex phenomena, the crucial questions can be formulated, which what was mentioned by Yuri Gurevich in one of his lecture, that the 2 main problems of computer science are what is the state and what is the transition relation. Of course, in the case, for example, of financial market, this is what we would like to estimate, talking about the risk. We would like to estimate the risk of this real situation in the physical world, and not this representation of this situation by the vector of values of particular attributes. Yes, so you should remember this. And also, this is also related to this question which are formulated about this necessity of reconsidering the basic model of computation. Here is the citation of people working in the quantum computing. What they are saying, that it seems that we have no choice but to recognize the dependence of our mathematical knowledge on physics. And that being so, it's a time to abandon the classical view of computations as purely logical notion, independent of that of computation as a physical process. So also in other areas like machine learning, for example, Vladimir Vepnik in this famous monograph about statistical learning theory in epilogue is saying that constructing the physical part of the theory and unifying it with the mathematical part should be considered as one of the main goals of statistical learning theory. And the very basic concept, of course, related to this complex phenomena are interactions. Interactions is a critical issue of understanding of complex systems, and we should remember that these interactions are going on between physical objects, and this what we are perceiving and representing by some information, some representations are only models. And in relation to this is a very nice sentence formulated by Professor Leslie Valiant from Harvard University, who also received the Turing Award. And he is saying that a fundamental question for artificial intelligence is to characterize the computational building blocks that are necessary for cognition. And these computational building blocks you can treat as this idea of this complex granules. But in this case, these complex granules are also related to perception. But if we are talking about perception, we are talking also about physical objects. And this discussion is also now actual in the community, discussing the necessity of modifying the concept of Turing test, because this Turing test, as originally conceived, focused on reasoning and language. However, problems of perception and actions were conspicuously absent. And now this community is trying to formulate this Turing test just to put together all this issue. So this main idea of interactive granular computing is to extend this granular computing by these interactions and reasoning about properties, perceived properties of these interactions, which are interactions between the physical objects, but also interaction between this informational abstract layers and physical layer of these granules. So for this model on which we are working, we can formulate several postulates, and I would like to formulate them in a very intuitive way, that the physical objects exist in the physical space and they are embedded into its parts. So this idea is related also to the idea of so-called hunks, which are introduced by Heller in his book. And the second is that physical objects are interacting in the physical space, and thus some collections of physical objects may create dynamical systems in the physical space. And some properties of physical objects or their configuration as well as their interactions can be perceived by granules, by these complex granules which are fundamental in our objects. So here is a very intuitive representation of the situation. We have these physical objects outside of the abstract space, which are interacting with the environment. And the question is how to perceive properties of these objects and their interactions, where, how, when to do this, how to generate the relevant configuration of physical objects and modify interactions between them. And also we should also take care of this, that perceived properties should be robust with respect to unpredictable interactions from environment. How this can be realized? So maybe I will, I have no time to go to the details, but this idea is the following, that each such a granule has informational layer in which this abstract information can be stored. And this abstract informations are labeling this what we can call specification of spatiotemporal windows or addresses. And we have also this physical layer in which we have this physical objects. And now is coming into the places what we call control of these granules. And the idea is like this, that these two layers are in some sense linked by this what we call informational granules or IC granules for short. You can treat them as a kind of the physical pointers linking this informational layer with some parts of the physical layer. And the aim of the control is to transform the actual configuration of such IC granules into a new one. These transformations may be related to creating a new these physical pointers, or maybe eliminating some of them, or maybe activating some, or maybe and so on. And so now the reasoning related to the basic cycle of the control is like this, that in this physical layer is in this abstract part is represented information, or we can say using this terminology, information granule, which is representing the current information about the perceived situation. And this basic cycle is like this, that this control is trying to check if this actual information about the perceived situation is satisfactory for triggering some transformation of this current configuration of the IC granules. If yes, this corresponding transformation is activated. If not, it's necessary to maybe enrich this information. This can be done maybe by extracting some information from the domain knowledge, or maybe from using also some physical laws, or it can be also obtained by activating some new informational granules able to perform some measurements, maybe preceded by performing some actions. So these are some maybe more formal ideas. So the most also important part is related to this, what we call physical semantics. So this can be described simply like this, that I have a kind of the rule which is related to launching of some transformation of these informational granules. And if I have this specification, I can submit the specification to this, what I call implementational module. And through this implementational module is making this physical implementation. So it's creating a configuration of physical objects, and by perceiving dynamics of this physical objects, we are getting the information which is encoded in this informational level or layer in this process. So this is also very important part of this model. So, and this what we can do now on this informational layer. We can aggregate this information. We can create this hierarchical classifiers, for example, and so on. Of course, in general, this control can be much more complicated. I have no time to just to discuss all these issues. This can be related to this set of rules that can be given in advance, or maybe can be learned about adaptive strategies, and so on and so on. Here is a general view of this complex granules. This granules, one kind of the granules related to this informational or abstract layer, and another is related to this physical world. So another picture. And I would like to say also a few words about this reasoning and reasoning in this model is realized over interactive computation supporting realization of perception. Perception as understanding the perceived situation to satisfactory degree for making the right decisions. So this is what I was discussing before. But there are some really important challenges here. Maybe I will only give you one example because of the short time, but these challenges were also observed by Professor Valiant. He was saying that a specific challenge is to build on success of machine learning so as to cover broader issues in intelligence, that this requires in particular a reconciliation between two contradictory characteristics, the apparent logical nature of reasoning and the statistical nature of learning. So in this way, as I am understanding, he is saying that we have a lot of challenges here. So first of all, this reasoning, which we call judgment, is covering not only deduction, induction, or abduction, but also is related, for example, to other areas. In particular, I would like to mention the experience. And this experience is maybe I will is related also to philosophy, and especially to the phenomenology created by Edmund Husserl. And here is a description about him, that he was frustrated by the idea that science and mathematics were increasingly conducted on an abstract plane, treating nature itself as a mathematical manifold that was disconnected from human experience and human understanding. And let me explain a little bit why this is important, that in this intelligence systems dealing with complex phenomena, we cannot cut the dialogue interactions with human experts, because this what we have as a practical judgment is not yet well formalized. We know very little about this. And here is a nice description of this. The practical judgment is not algebraic one. And at the end is that this identifying things of importance from a potentially endless pool of candidates for making decisions is well beyond the jurisdiction of reason. Another way of expressing this you can find in the work by Professor Melanie Mitchell from Santa Fe Institute. She spent very many years on complex systems, and she is talking about the one aspect of this practical judgment or experience, the quest for machines that can take abstractions and analogies, reasoning by analogy, is as old as AI field itself, but the problem remains almost completely open. And I think that this is also the reason that what I observed in the lecture by Professor Roman Słowiński, that he, when he was talking about this evaluation made by expert or by humans, we really may not understand how they are doing this. So this is very important. But there are very many other issues which are very important for considering in this reasoning. Among this is this idea of information granulation mentioned by Professor Zadeh in the context of strategy of divide and conquer in human problem solving. And this has also, I will shortly finish, has also impact on the understanding of fuzzy sets and rough sets from the point of view of reasoning toward membership estimation. And this what was we considered so far. These information tables or information systems were abstract mathematical objects just completely in this abstract space. But now when we are considering them in the context of the control of these complex granules, we should consider that, that this, what we were treating as objects are informations which we obtain by interaction of this icy granules of these physical pointers with the specific parts of the physical space. And the same is with fuzzy sets, that if we consider a fuzzy sets as a membership function from the mathematical set X into interval 0, 1, we are cutting the connection of these models from the physical world. However, this is only the part of story for fuzzy sets, because really this what we would like to estimate is a membership degree, not of this representation of the state, but of the situation in the physical world, which maybe temporarily we are perceiving through this vector of values of particular attributes, but maybe this is not relevant, and this is raising a lot of questions. So this work on this foundations of interactive granular computing, I am treating as a very fundamental for this information intelligence systems dealing with complex concepts for the rough sets, for the fuzzy sets, for the risk management and other areas. So in summary, I would like to say that I was trying to outline some aspects of interactive granular computing and perceptual approach to intelligent system, or even to artificial intelligence based on this interactive granular computing. We discussed these models as a base for design intelligent systems dealing with complex phenomena. The aim was to explain how the interactive granular computing model has the potential to handle the grounding problem by bridging a connection between the abstract mathematical modeling and real physical semantics. And also I was trying to emphasize the importance of reasoning, and in this reasoning we have a lot of places for the research, because this what was developed so far in the very many branches of logic is still not enough for this kind of reasoning which is necessary here. So here is some references, and with this I would like to thank you very much for your attention. Hello, can you hear me? Hello? Hello? Hello?
I use that. Yes, thank you, Andre, for your overview of C granules. I mean, this is your idea, we know, and you are involved in this for quite some time. And you have given just some glimpses of your ideas. There are systematic developments of some of these ideas, some parts of these ideas already done that I know, but I would like to invite a few questions or comments or clarifications from the audience. Any question, any clarification? Well, maybe if I ask one question, then some other questions may be generated. You have, Andre, you have mentioned from physical to informational content. Have you developed any idea of how, general idea of how this physical phenomena can be translated into informational phenomena, informational content, so that ultimately these granules, complex granules, can be really built? Do you get my point?
Yes, yes, of course. Of course, we have this kind of the knowledge. For example, let's assume that I would like to make the picture using camera of the object which is in a long distance from me. Okay. So in this case, what kind of this physical objects can be involved helping to solve this problem? What kind of the configuration of physical objects I can create? I can, if I can assume that I have, for example, a cellular network, and I can send from this informational layer, I can encode the telephone number to the pool of robots, asking a robot to move a camera close to this object, yes. And if I create the, if I assume that this cellular network of phones is working properly, so after a while, this message after encoding will reach this, say, pool of robots. And if this robot is able to understand this order, is moving to the specified part of the physical world, is making a picture, and next the second task is to organizing sending back this picture to the C granules requiring this. So in this case, I can assume that in advance I have through this experience of constructing some configurations of objects and having this experience that if I will properly initiate interactions about this object in this network, after a while I will receive information which I can interpret as information about the objects in the long distance. Another kind of the information can be obtained about objects which are directly accessible by C granule. In this case, this information is possible to obtain by direct measurement. Like, for example, I would like to check by hand if this cup is hot or not, which is very close to me. Okay, so just in this reasoning process, which is involved about the correctness of this construction of this configuration of physical objects, requires to have this database of domain knowledge or physical laws which are supporting my reasoning, that if I will initiate this properly, this implementation procedure, after a while, if maybe nothing dangerous from the interaction with the environment will not happen, I will receive the required information. So, of course, so this is, of course, in more complex situations, this may require also to some complex reasoning about attention. It means that if I would like to perform something, or maybe if I would like to measure something in this complex situation, I should specify where I should do this, how I should do this, and so on. Okay, so this is related to this issues of attention, which is also discussed by many researchers, not only in cognitive science, but in other areas like robotics and also now in deep learning also.
Okay, thank you very much. We are here, we are getting hungry gradually. So I think we should close this session now. Andre, thank you very much for giving
I would like to
sharing our ideas.
Congratulate Yumi here,
Yeah.
because recently I would like to maybe say that this was a good news, that the habilitation of Shama was approved by National Committee. So congratulations to you as
Yes,
a supervisor.
I know. It's a very good news. Okay, thank you very much for giving this talk, and I also thank this audience now. So over to the organizers.
Thank you. Thank you for chairing this session, Professor Mihir Chakraborty, and we would like now to express our appreciation of your participation here by offering you a little memento. And I request Professor Shamarjit Kaur to come onto the stage. A round of applause for Professor Chakraborty. Yes. Okay, thank you, Professor Chakraborty, for your participation. And now we end this second session, and we are going to reassemble at 3:45, just at 3:45 after lunch. Okay. As early as possible, maybe 3:35 or 40. Yeah, because yes, we are running late. Yes, 3:35 to 3:40. Our guests, please have our lunch in the green room behind the auditorium, and others at the executive hall. Thank you. See you at 3:35 to 3:40. Oslan Sachin. Welcome back. Please be seated, all of you. And I now request Professor Manoranjan Maiti to take the stage. He will be chairing this session. Okay, so I have the pleasure to introduce Professor Manoranjan Maiti. He was a distinguished professor at the Department of Applied Mathematics with Oceanology and Computer Programming in Vidyasagar University, Midnapur, West Bengal, India. He did his PhD in Applied Mathematics in 1970 from University of Calcutta, Kolkata, India. He worked in Indian Institute of Tropical Meteorology, Indian Space Research Institute, and Vidyasagar University in India. 20 students got PhDs in operations research under his guidance, and at present, 10 students are working as scholars, PhD scholars. He has published more than 200 papers in international journals in mathematics and operations research. His fields of interest include operations research, fuzzy mathematics, fuzzy and rough sets, etc. We are privileged to have him as sessions chair. So I now ask Professor Maiti to take over from me.
Good afternoon to all. Now the session 3. We are in the session 3. The first speaker is Professor Vasavi Chakraborty, IIT Prefectural University, Japan. Let me. Let me introduce Professor Chakraborty. Professor Chakraborty received BTech, MTech, and PhD degree in radio physics and electronics from Calcutta University, India, and worked in ISI, Calcutta until 1970. From 1991 to 1993, she worked as a part-time researcher in Advanced Intelligent Communication System Laboratory in Japan. She received PhD in Information Science from Tohoku University, Japan in 1996 and worked there as a postdoctoral research fellow until 1998. She joined as a faculty in the Department of Software and Information Science, IIT Prefectural University, Japan in 1998 and served as professor and head of pattern recognition and machine learning laboratory until her retirement in March 2022. Currently, she is a distinguished professor and professor emeritus in IIT Prefectural University. She also holds the position of Dean and distinguished professor in School of Computing and Madanapalli Institute of Technology and Science, Andhra Pradesh, India. Her main research interests are so many areas, including pattern recognition, machine learning, soft computing techniques, and so many things. She received so many, she is a live member of several institutions in India and outside India. I welcome her. Madam, 30 minutes, as we are late, 30 minutes, 25 minutes for lecture and 5 minutes for questioning. I request Professor Chakraborty to start her lecture.
Thank you very much for the introduction. So today's my talk is on the topic quantum enhanced machine learning algorithms for optimal feature subset selection. I'll try to be as quickly as possible. I'll try to deliver this talk. So Now, what is the feature subset selection problem? Basically, in pattern recognition or machine learning area or data mining or any data analysis, we have lots of data and we try to classify or cluster. That is, in a supervised way, we try to recognize the data, or in unsupervised way, we try to recognize the data, or prediction or any sort of data analysis. When we have a large number of data with huge dimension, too many dimension, then all the dimensions are actually not necessary for the task, for the classification or the prediction or whatever be the task. It is not necessary. And on the other hand, if there are unnecessary information collected in the data, that actually disturb the classification process. So, so we need to select the appropriate informations. So that is basically is the objective of feature selection. So selection of the subset of relevant features. So what we want to do, we have a high dimensional data. We have to reduce the dimension of the data. One purpose is to remove the irrelevant and redundant features. And that's why we will get the dimension. If the dimension is lowered, then the computational cost for the further processing for the task of classification or clustering or regression, in that part, the computational cost will be lowered. So, and of course, this has other side effects also. More features need more samples for successful training, and overfitting training. This training time also takes larger training time, and which affects the performance of the system. So basically what I want to say is that from the high dimensional data, it is absolutely necessary to find out the actual important dimensions and informations of the data, and that is called as feature subset selection. So for a large set of features, we have to reduce the feature set to a subset of the features. Now for that, for doing that, the computational process is in two steps. One thing is that you have to retain only the important features. So you have to evaluate the features. So we need some evaluation metric for evaluation of the features. And then with that evaluation, we have to retain the optimum feature subset. So finding this optimum feature subset is difficult, because when we rank the features according to their goodness or something by evaluation metric, the first two features in the rank may not comprise the best two feature subset of the two features. That is a finding that was found out in 1973 by Cover and Hart. And for that, which feature subset will give the best performance, that depends on evaluating, that you can only find by evaluating all the possible combinations of features. So the problem actually turns out to be an NP problem or an optimization problem when the number of features is very large, because if the number of features is n, then the total number of subsets n, these possible subsets will be 2 to the power n. So there are actually, this problem has started with the pattern recognition area of applications, and it has a history of more than 50 years. So lots of feature subset selection algorithms have already been developed. And mainly those algorithms initially started in the area of statistical field, and then in soft computing and with the different types of tools, these feature subset selection algorithms are now available. If I just summarize all the algorithms, they are in terms of evaluation, they have these three types: filter, wrapper, and embedded, which actually in the wrapper, we use the classification accuracy as the evaluation function. In filter, we use some intrinsic data quality for evaluating the features. And embedded, we can use the two hybrid type of approaches. Now with the selection type, for the feature selection, we can do feature ranking. That's also one way of feature selection. You can just evaluate the features independently and then rank the features, and a percentage of top features you can take for for processing of the second stage. But another is you have to find out the best feature subset or developed a more quantum-oriented feature selection algorithm, feature subset selection algorithm, which can be run on a quantum computer. So I will give a short account of these algorithms which we developed. So this is the basically owl search algorithm. Owl search algorithm. Owl search algorithm actually is a meta-heuristic algorithm. It optimizes with by copying the owl's characteristics of finding out the prey in the night, which actually the owl does by calculating the intensity difference between its two ears, from right ear and left ear. So from the prey, it calculates the distance of the prey by the vibration or sounds coming from the prey to the owl's right ear and left ear, and by the difference of the intensity, it finds out the location of this prey. So these characteristics is used in the owl search algorithm as a meta-heuristic algorithm, and these are some of the equations actually used in that algorithm. Basically, the owl, we find that this is a population-based meta-heuristic. So the population is the owl's positions. So owl positions are initially randomly initialized. The fitness function of the owl is actually proportional to this intensity difference, which actually the algorithm considers. Intensity is proportional, inversely proportional to the distance of the prey. So what actually does, the prey moves and the owl finds out the prey's location by the intensity difference, and by that way the owl also moves and update its position. And finally, the solution is actually the owl's actual position, how it actually captures the prey. So when we model it to a meta-heuristic algorithm, basically what we do is that the solutions are the initial solutions are the owl's positions, but the best solution is the prey's position. Now the owls, that is the initial solutions that move, that update in every cycle by calculating the fitness function and the distance between the prey and its present position, and at every round it updates its position, and finally after some round, when you finish, the algorithm is finished, then the best position, that is the best nearest to the prey's position, that is considered as the final best solution. So this is the basic way the algorithm works. Now this is actually the flow chart of the algorithm. First, initializing the population of owls, and any meta-heuristic, there are lots of meta-heuristics algorithms, and most of the algorithms have some parameters which we have to control. We selected this owl search algorithm because this algorithm has only one parameter which we need to tune, that is this eta. And so it is randomly selected and we have to tune it for the particular problem. So the fitness function is values of the owl are calculated and find the best and the worst owl and prey, and then updating the position of the owl every time we calculate the fitness of the owl, and the best fitness actually is the global best solution. And finally, if the stopping criteria is met, stopping criteria is either a fitness value, we predefined limit of the fitness value, or we have some predefined epoch. So depending on that, we'll stop. Now we changed it to a binary version, because originally the owl search algorithm was used for continuous functions. As feature subset selection problem is basically a binary problem, that is whether we use this feature or we do not use this feature. So the total dimension, we actually consider the problem in a binary space. So the feature which we consider is 1, and if we not consider this feature, that will be put at 0. So the whole algorithm is modified with this point in view for the classification accuracy of BOSA Q3 with other actually meta-heuristic based popular algorithms, that is geometric algorithm, particle swarm optimization. So compared to those algorithms, we also found that for most of the data sets, the proposed binary owl search algorithm with the Q3 transfer function gave better classification accuracy. So this is some results which show that with this BOSA Q3 compared to the other BPS or BJ, we can select a lesser number of features. So final feature subset contains less number of features. This is also the computational time. For computational time, BOSA Q3 is not very good, but it is comparable to the other algorithms. And so we actually did some statistical tests, and finally we just could conclude that this proposed BOSA Q3 is not bad than existing meta-heuristic based feature subset selection algorithms. These are the paper published in these things. Now we extended this BOSA, I've proposed a modified BOSA, where we actually, in the original OSA algorithm, there was no concept of this elitism mechanism or mutation operation or changing the parameter eta with the process of epoch. It adaptively changes the parameter by itself. In original OSA, the parameter eta was fixed at the beginning and it was fixed for up to the end. But we changed it when the process for the process in between the process, and we introduced a mutation operation and elitism mechanism which are available in GA, in fact. So getting idea from that genetic algorithm, we introduced these operators in owl search algorithm, and we named it MBOSA. And so what we did, we actually dynamically changed that parameter. And why we changed? Because sometimes we found that the convergence of the algorithm is sometimes stuck at a point. So to getting out of the process from stacking, we actually changed this eta with the time, with the iterations. Eta is changed there. And then it is not moving. Why it is not moving? Okay. So, by this we just changed the we introduced some other characteristics into this algorithm, which is elitism and mutation. Mutation is just in GA we use, sometimes we just flip some of the values. And with this introduction, the algorithm is as it was same as this previously, but just with the introduction of these operations. And the results we got, it's a little bit better than the original BOSA, this MBOSA. And we use the same data set for these results. This is the average classification accuracy. Classification accuracy is a little bit better than our original BOSA after introduction of these new parameters in this MBOSA. Average feature subset selection ratio, we get actually here we get a good result because the final selected feature subset has lesser number of features here. This is also some statistical tests we did to test that whether our result is statistically significant or not. So this is the results. And finally, actually, what I want to emphasize is that we tried to use some of the concepts from the quantum computing into our feature subset selection algorithm. In a sense that in feature subset selection algorithm, when actually number of features is very large, even if we use this MBOSA or Q3, the computational time is very high. So as quantum computing can give some effect of parallelism, so we tried to use some of the concepts from quantum computing to find out whether these algorithms have some computational speed up or not, to see that things. So these are actually the slides to explain some of the concepts of quantum computing. The basic concepts actually it is initially our algorithm in classical feature subset selection algorithms, we represented one feature by a bit. Now here we actually represent it by qubit. So qubit and bit is difference is that bit actually represents either 1 or 0. Qubit can represent, it is a superposition of 1 and 0. That is the first basic concept in this quantum computing. So that concept to use, and other two superposition, and another concept to use is measurement. When we actually model the whole problem to a quantum concepts, and then when we calculated it in classical. So when it actually measurement, after that it actually converges to a classical bit, either 0 or 1. So we did another algorithm, we actually developed this quantum inspired. We call it quantum inspired because we didn't actually use quantum computer to solve our problem. We used it we actually calculated or simulated in classical computer, but we use some of the idea of quantum computing here because each feature is represented by not a binary bit, it is actually a qubit. And for initialization, that is initial population, we used Hadamard gate. This gate idea is from this quantum computing, and actually those gates are implemented by some matrix. So what we used, we calculated with some matrix. So our initialization process in classical version of the algorithm, and this version of the algorithm is a little bit different. That is the difference between our proposed algorithm and the previously proposed algorithm. And then we used for updation of the owls in every epoch, we used quantum rotation gate and quantum rotation gate. So actually we use two types of gate. For initialization, Hadamard gate, and for updation of the owl's position in the binary space, that actually we used quantum rotation gate. For fitness function, we used wrapper-based fitness function. And for measurement also, final measurement also, we used measurement gate of the quantum concept. We tested this algorithm with some data sets. Those are public benchmark data sets, and compared this algorithm with normal, generally more popular, this GA, PSO, and this. And here actually for classifier, we used K nearest neighbor. And so these are the some mathematics beside this quantum gates. I'm skipping the mathematics. These are basically finally some metrics we had to multiply. And so I'll go to the algorithm. So here our algorithm is from starting with we have a population. First, we need to generate a population of owls, which are the first solutions, possible solutions. So we actually, by the Hadamard gate, we initialize it with quantum population that is represented by qubit. And then we actually, this binary quantum owl population, for fitness evaluation, we use measurement gate, and then we put it in this normal classical values and calculated the fitness. And depending on the fitness, we use some rotation gate. We calculated the rotation value and uses this rotation gate to find out the new positions of the owls. So this is the new quantum owl population. And then we again calculate the fitness value, and if the best fitness fowl is actually returned as the best value, and then we try to check whether the stopping condition is achieved or not. If the stopping condition is achieved, then we'll stop. Otherwise, we'll again do the population based owl position. If we do not stop, then we'll again try the new population, and we again do the fitness evaluation, update the evaluation, update the those population, and then again search for the fitness and for the stopping condition. So this is actually the whole algorithm where you used some of the gates, and this implementation of the gates are in matrix. And then this is the quantum concepts which is introduced in the whole algorithm, and we named it quantum inspired strategy. And in this particular algorithm, we used for fitness evaluation, we used the classification accuracy. These are the description of the data sets we used for testing our algorithm by simulation. And these are the average classification accuracies we get. So for our new algorithm here, this is our original algorithm, and we got a little better accuracy for some of the data sets. On the average, we get better accuracy. But when we tried this is, I think, average feature selection. What are the number of reduction? That's percentage of reduction of the features. And this is, I think, computational time. Computational time wise, actually, it took a long time. And especially when we tried with bigger data sets with higher dimensions, then it took a very, very long time. So we actually transformed it. Actually, we tried with microarray data sets, which is high dimensional data. And with those data, if we use this quantum inspired strategy with wrapper functions, then it took a long time. So we tried to convert it into two-step algorithm. In the first step, we did some filter ranking, and we use some filter approaches for ranking of the features. We used actually 5 filter approaches with ranking, and first top 20% of the features we took, and then we did voting. And then from the voting, we selected the first, selected some of the features, the top ranking features. And with this selected feature, we then use this quantum inspired owl search algorithm with this fitness function. So the algorithm is like this. First, we started with the data set, and we used some filter functions to find out the top 20% of the, actually not 20%, depending on the data set we selected, how many feature we will select. So, and with the result, and from this top genes, we did some 5 types of filter functions we used, and with the voting, we selected the top features. And then we did this quantum inspired owl search algorithm, but this time we didn't use the classification accuracy and the fitness function. We used some filter based objective function as the fitness function. And from there, you select the final feature subset and evaluated by some classifier. So here also the same thing as the previous algorithm. For the representation is quantum representation by qubit. Measurements also use quantum gate. Rotation value calculation and updating mechanism and measurement, we also use some quantum gates. And the feature fitness function, which we use this mutual information based feature selection. These are already developed filter functions which are used in many feature selection algorithm previously. So these data sets are used for the simulation experiments. So these are number of features, number of instances, number of classes, the information about the data set. So here also we found in here that according to the classification accuracy, this new algorithm, this filter based quantum inspired algorithm, that is no better than this wrapper based algorithm, but the number of features selected is quite less here. So that is the time. Computational time also is lower, and the number of features selected, final feature selection number of features are lesser than what we got in the previous algorithm. So this is the result. These are some statistical tests to find out how the variance and the algorithm works. So these are some of the comparisons with not our algorithms, but existing algorithms. We did some simulation with simulation experiments. We did some comparison with the existing algorithms. So finally, what we did, we tried to find out a method which is more based on quantum computing based method for this feature subset selection. Actually, any optimization problem can be transferred to QUBO, quadratic unconstrained binary optimization. And we tried to and then quantum computer based on quantum annealing that can solve this QUBO. That is already established fact. And what we tried to formulate our problem, our feature selection, subset selection problem by a QUBO function, and then try to solve it not in a actual quantum computer. We used a simulator, quantum annealing simulator, and then solve the problem there. So this is our process, and we use original simulated annealing in classical concept with classical simulated annealing, and then we use the simulated quantum annealing, which we actually run on a quantum simulator, Squad Solver, and the result we got is actually we use these three filter subset selection functions, this MRMR, minimum redundancy, maximum relevance, joint mutual information, and correlation based filter. These three are actually three popular algorithms for classically feature subset selection algorithms, for filter based feature subset selection algorithms. We tried to convert this matrix into some QUBO format and tried to solve it in Squad. So these three functions. So what do we finally got? We did simulation on these data sets. And so this is the QUBO matrix for U-Poly data set. So this, and finally what we got is that we compared it with original classical simulated annealing used on those feature sets and the quantum simulated quantum annealing for feature subset selection solved on a simulator. So the main difference we got that we couldn't actually, due to the constraint of time, it was quite time consuming. So for the time, from the computational time point of view, actually it took longer time. But one thing we noticed that here, when we do this, we run this algorithm for in various run of the algorithm, the optimal feature subset that came out that differs. That subsets are not stable. But while in SQA we solve, all the time we got the same feature subset for the output result. One thing is that actually this actually outputs after 100 run. So that may be a cause, but we think that if we can do it computationally more effective, in a more effective way, we can get a more stable feature selection algorithm. Actually, feature selection algorithms are, we try to develop some efficient algorithms, but the definition of efficiency or definitions of good algorithms are that we try to have a classification accuracy, high classification accuracy, of course, but at the same time have lower a number of features in the final subset. And another thing also is very important, that is the stability. The stability we didn't consider in implicit way, or in explicitly, we didn't consider in our optimization the concept of stability, but concept of stability is also important, because if we run the algorithm several times or with different training set, and if we get different types of feature subset, then that algorithm is not stable. And if we use those feature subset for the processing of classifier, so that also will vary, the result will be varied. So from this experiment, one thing we noticed that if we can use this classic quantum computer for solving this this type of feature subset selection problem, there is a chance that we can get a stable feature subset selection output from from these algorithms. So these are some statistical results for this, and this is also presented in this conference. So this is all which I can tell you. So thank you for your listening, and if you have any questions.
Thanks to Professor Chakraborty. Any question from audience?
I have a small question. Question is that regarding the computations of the, because here you are using this bit actually, but you are applying the qubit. If you can little bit elaborate that this matrix form, what kind of matrix by which we can apply in the computer, because here we cannot apply the quantum computing directly. With the help of bit, actually we are computing this qubit actually. So if you can a little bit elaborate that, how this can.
Actually, I didn't. Those elaboration will take possible.
Little bit, just brief actually.
Few lines.
If you just, we represented it by a qubit. So representation is compact. So in that way, the representation is compact. But when we initialize that, then the calculations are done in that with a qubit. But finally, when we calculate the fitness evaluation, the qubit is that time converted to bit, normal bit. So fitness evaluation is done in classical way. And then again, when we do the update mechanism, we use these gates again, rotation gate.
My point is that whenever you are applying this is this Hadamard kind of.
Yeah, Hadamard gate we used in the first for initialization.
Hadamard gate means this is a conceptual Hadamard gate or actual Hadamard gate?
No. This is the matrix only. Yes.
Conceptual point.
Conceptually, yes.
And I can say that we have same process we have used, and Professor Maiti, in GA, genetic algorithm, quantum-based genetic algorithm. It has been published in computer and industrial engineering.
Yes, and that was the actual inspiration of our work.
Oh,
quantum GA.
Okay.
That was a paper in quantum GA.
Okay.
Yeah.
Our liver has.
Yeah.
Okay. Thank you very much. Any other question?
So one more thing. So basically, what you are doing here is hard. We hard basically means that it is not at all empty. Even whether it is empty also we do not know. But it is as hard as empty complete. Okay. So that kind of problem by combinatorial kind of thing. So we are trying to solve with the help of this computer, this quantum computer.
Yes.
Am I right?
Yes. In a way, actually, we are solving this in different way. In this type of problems, we are solving with meta heuristics originally, with this GA or PSO or whatever bit, this OSI, this owl search, also this. So adding some more concepts into that, whether we can solve it more quickly or more efficiently, that was our searching. Yes. And what is the concept of best is that it will give the classifier accuracy also highest. We have the number of features also short, and at the same time, the final output will be stable.
You can apply this to population-based heuristic methods. Okay, now time is short. Any other short question? Okay, I had some question. I will discuss with you later.
Okay.
Thank you to Professor Chakraborty for a nice lecture. Please join hands with me.
Thank you, madam, for your presentation. And I would request Professor Shomajit Kaur, the program chair, to come onto the stage. And as a mark of appreciation, we would like to offer a small memento to madam. Please. Thanks.
Glad to meet you because I was very much happy with that.
Okay, our next speaker is Dr. Subodip Bandyopadhyay. He is scientist in Ericsson, principal data scientist in Ericsson. I think it is on online. Hello, Dr. Bandhavada, can you hear us?
Can you hear us, sir? Hello?
Hello, can you hear?
Professor Bandhavada. Oh, he cannot.
You cannot hear.
Please, yes, please wait. Can you hear us? No. Telephone. Are we in touch with him by telephone? Maybe he should be asked to unmute himself or something. If he's trying to say something, could be, yeah. No. Professor Kaur is trying to contact by telephone. Please bear with us. Yes, we'll. Hello, can you hear us? Oh, Professor, he's speaking to Professor Kaur. Yeah. Rejoin. Acha. ওনাকে একটু মেসেজ করুন।
Am I audible now?
Yes, you are. Are you audible? I mean, are we audible? Can you hear us?
I can.
Yes.
I can hear.
Okay, welcome, Professor Bandhavada. Can you hear me?
I can hear you.
Okay, thank you. So, let me introduce Dr. Subodhip Bandhavada. He is the principal data scientist at Ericsson. He did his postdoctorate from ISI, Institute of Statistical Science, Taiwan, did PhD in statistics from ISI Calcutta, master and bachelor's in statistics from University of Calcutta. He has worked more than 9 years in academic and industry and research and development organizations. Welcome, Dr. Bandhavada. Now, due to the time short, your lecture will be on 25 minutes and 5 minutes will be the questions. I request you kindly commence your lecture. Please.
Yes, I'll share my screen now. Let me know if it is. Not yet. This is really amazing. Please confirm if you can see my screen. Can you see the presentation?
We only see your face.
Oh, that's very unusual.
Yeah, take your time, please. Take your time. Yes.
Let me just.
Yes, sure.
I'm not very sure what is happening, why it's not being.
Oh.
Just a moment.
Yeah, sure.
This is very, very awkward. I am sharing my screen, but nothing is being shared, it seems like. What can I
you
do
try
is that
Appress? Can you try Appress?
What is that?
Start from beginning, you can.
Okay.
You start from the beginning again.
I'm sharing my screen, but it's not somehow being shared. What can I do is that I'll just quickly mail this presentation to Professor Kaur. And in the meantime, I'll just try to share. If it doesn't happen, then if it is possible to share at your end, that would be great.
Where is Professor Samarjit Kaur? Could someone please call him inside? Mail ID to বলবেন বা ওনাকে পাঠাতে আপনি ওনাকে লিখতে বলবেন we are trying to send the system email ID to you so that you can send it to us.
Okay, that's great. That's great.
Yeah,
you
just
can,
one.
You can text me also. You can text me my phone number. I can share.
I think email is fine. Send.
Okay, let me know which mail ID I need to send it.
Yeah, it's reaching you.
Okay.
He's trying by comment. Yes.
Hello. Hi, Professor Kaur. Hello.
Send. Yeah, the ID has been sent to you. Jilam Das.
Okay, I'm just trying now. Let me just. Hello.
Hello.
না না আমি ওই জন্য একটা মেল আইডি এক্সপেক্ট করছি ওরা বলছেন মেল আইডি পাঠিয়েছেন সো জাস্ট এক্সপেক্টিং দ্যাট মেল আইডি টু অ্যারাইভ I'm just hold for a while.
Could you try to rejoin? I mean, that might help.
I'll do that. I'll do that. In the meantime, I'll send this PPT to Professor Kaur's mail ID because I have not got all yet this one.
Oh.
Okay. 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 Fine. Thank you, Professor Kaur.
It has come. Is this the screen? Quantum I for C? Oh, no. Oh, sorry.
No.
Oh, sorry. It's yours. Yeah.
I have sent the PPT to Professor Kaur in his mail ID.
Okay.
He will share shortly. Because I didn't receive any mail yet. This is little awkward. I'm sorry for the inconvenience.
Yeah, okay.
Okay.
Please, could you share the entire
I'll do
screen
that.
with
I'll do
us?
that right now.
Yeah.
I think I got the mail ID. I'll
Okay.
share here only.
Maybe rejoining might help. Yes.
Just a moment. I'll do rejoin right now.
Yes. Screen is? Yeah, I've been asked to freeze it. Yeah. हाँ, ठीक है.
Please note, I have sent the presentation to the mail ID shared in the chat. Probably it has reached by now.
Yeah, we are checking. Has it? Achha. Unfreeze. Hello, sir.
Hello?
Yeah, we can hear you.
Okay. Okay.
Sir, can you hear us?
Yes, I can. Can you hear me?
Yes,
Yeah.
we can hear you. And the screen shows your material. Yes.
Okay. Okay. First of all, sorry for this glitch. It is something which nobody has control. So still, I'll say that sorry at my end, and I am privileged to be invited to deliver this talk here. Thanks.
Okay,
everyone.
please commence your lecture, and time is 25
The
minutes.
content that I'm going to cover is briefly given there. So I'll just try to draw some similarity, some connection of the telecom domain and the optimization techniques which are omnipresent here. It's a very vast domain, and it has multitude. It can be looked from different perspective, and hence the requirement or the application of any technique is very much subjective. So what I'll try to do is to give an overview, and then I'll deep dive on 2 different methods, and we'll see how these are like. This is connecting with everything. Okay, next slide, please. So in brief, this is how our telecom landscape is defined. It has 3 main players. One is telecom technology provider, then there is service provider, and there is end users. And technology provider provides the technology infrastructure, everything to build and set up a telecom network and to run it. Service provider utilizes that network to cater the end users, like individuals like us, or maybe some enterprises, in different ways, either it's voice or in data, or currently probably in many other ways like AR, VR applications. So the technology provider view and service provider view, we see they are different, and hence the type of optimizations that might be required, that might be utilized at individual ends are different. For example, technology provider view might be more inclined towards to optimize the performance of network, and that will invite different pockets of applications, whereas the service provider would like to give the best quality at best price. Hence, the objective and the techniques might be different there. Next slide, please. Next slide, please. Yeah. So roughly, you can say that the technology provider, the telecom technology providers' need for optimization is in 2 distinct functionalities. One is that the network related technology and support functions, other is non-network functions. In network related, there are planning, there are design, there are deployments, and then post deployment there are performance assurance and maintenance scenario. And in each subfield of these, there will be different applications of optimization. For example, when a design is being created, then the idea might be how we can optimize the locations of different cell towers so as to provide the best service in the geography. Whereas when not some of the network related aspect, like for example customer management, then it might be as simple as how we can optimize or maximize the customer acquisition and maximize the retention and minimize the churn. So all these things in some or other is they are linked to the optimization technique that are being applied in telecom, which is omnipresent. Next slide, please.
Yes.
Yeah.
Oh, it has been put.
Oh no, this is. I think this is a wrong. This is a wrong one that I have shared. I'm sorry. Can you please wait? I'll share the one that is currently I'm using. This one, can you please delete it? This has some informations which I should not actually share. Can you please delete it? I'll share the one that is required now. Please help me for a while.
Please.
I have sent it in that same ID, Chilam Das.
Yes, we are trying to locate it. Yes. Yeah, got it. Just wait, please.
So one request, if you can please delete the other copies, that will be great.
Yeah, delete the other copies. Yeah, they are deleted. Yes.
Thanks a lot.
Yeah, actually, we have to freeze and unfreeze, so that takes a little time. Yeah.
That is okay. Actually, at my end, it was a mess. So there are multiple files open. So I just thought that I'll present at my end by choosing the one that is the right one. Anyway, sorry for the inconvenience.
Yeah, it's okay. It's okay, sir.
Maybe this is the first and last time I'm presenting virtually. Next time I'll choose to go physically. Yeah.
Yeah, it's difficult sometimes.
Yes. Yeah. So I think we were in the sixth, probably in the sixth slide we were.
Yeah, we are trying to arrive at the sixth one.
Right. So I'll be quick. So we'll be considering two different use cases, which are like a very primary applications of optimization technique in telecom. If you go to previous slide, I'll just the previous slide. Yeah. So this is a typical site of a telecom tower. We all know that, and there are different power sources. The power sources are mainly the electricity, the default one. There will be diesel generator and there will be battery. Now the whole point is how we can optimally choose the source depending on the requirement of the network, so that it will run long. It will be providing the power source whenever it is required. There will be a smoothness, consistency in the power source provision, and on top of that, it will be cost effective and environment friendly. So next slide, if you can go, please.
Slide.
So this is the premise. So usually in any tower there will be multiple sources, and the whole idea is to make it so automated that we'll be meeting customer optimization, we'll be meeting improved service and sustainable development goals. Like it will be more green, we'll use less diesel power sources, and not only that, we'll be utilizing battery with a good amount of storage as well as good amount of utilization. That means if there is a provision for using the battery for next 1 hour and making sure that we have enough storage for any kind of sudden power failure, then we should actually use the battery for 1 hour. Why I'm emphasizing on this particular point is, in general, there are non-static kind of optimization scenario where it is always a rule based. So you first use whenever there is electricity unavailable. So first you then use diesel generator, and when diesel generator is not available, use battery. And by doing that, we are unnecessarily overuse the diesel, and the green concern is seriously hurted. The cost is higher, and not only that, we are not utilizing the battery properly, and hence the battery life also gets affected. So the whole solution here that we have proposed is a very much intuitive. It's a contextual. So what we have done is we found out the usage, the different types of usage that a particular site has, and depending on that, in next 2 hours, what are the load profile of the battery of that particular site, and what are the cost profile of different power sources. And depending on that, we have identified what might be the preferred period or preferred intervals in which we would like to provide a particular type of power source, subject to condition that we are optimizing the cost, we are minimizing the cost, and also we are optimizing the battery usage. And that brings a manifold value. It's a lot of value to the technology provider, to the service provider, to the end user also, because it takes care about the optimization of the cost, it takes care about the continuity of the service, and it takes care about the network quality also. Because if service is continued, then network will work flawlessly. There will be no power shortage and hence any disruption. And it has a high concern of the environment. So if next slide, please. As I mentioned, we'll profile the cost, and then we'll find how we profile the cost. So now at time point set t, I'll just find out for next 2 hours what are my expected usage or load in terms of electricity requirement, and then we'll also figure out what are the cost, and then we'll find what is the best period, what is the period where which source is giving us minimal kind of cost, and hence we'll choose that. Next slide, please. Yeah, so this is a typical depiction. It says that, so we start with say the time point, the current time point, and we are predicting it in advance, say maybe 15 hours in advance, 15 minutes in advance, and we are predicting it for next 2 hours. The horizon is 2 hours. Typically the profile will give us this kind of intersecting scenario. By the nature of battery and DG, when we profile it cost, then it shows that the battery usage has lower cost in first few hours, and then it increases, and the opposite is the DG. And this depends actually on many things. The main novelty of this approach is how we are actually profiling this cost, because this cost profiling requires consideration of the impact of battery life on battery usage, battery usage on battery life. Not only that, the DC uses and maintenance, all those things are kind of compressed into this cost profiling, and that gives us a clear kind of decision point where we need to switch from one source to another, and that's what we are doing in this case. Next slide, please. And this is a depiction of how it runs. It actually runs in continuation. It runs and churn out recommendation for next 2 hours. That means at which time to which time in next 2 hours, which source should be used. And it does the same at every 15 minutes. And all the recommendations of earlier one is overruled by the current 15 minutes, because while recommending the sources at current time point, it takes care about all the changes in data, and hence that recommendation is going to be the optimal recommendation. That's how it happens. And once that is done, then architecturally we actually publish that result to some automated system, and the system takes care about the closed loop actuation of the whole thing. And hence what happens is that every 15 minutes it churns out recommendations, and those recommendations are utilized whenever there is a shortage of electricity and there's a need of choosing the alternative power source. Hence with this I'll just briefly go on the next one more use case, and which I'll close as quickly as possible. Next slide, please. Yeah, next slide. So this is optimal remote electrical antenna tilt. So this is a common feature in a case of an electrical antenna tilt. We have electrical antennas in mobile towers, and it works like a floodlight, like the beam of electromagnetic induction, whatever comes through which we get our signals, that actually that transmission happens just like a floodlight. If we tilt the floodlight up, it will go for further, but it will lose the foot, and it will also lose the intensity. The same happens for the antenna also. And if it tilted down, then it will it will have less coverage, but the quality of coverage, that means the intensity will be much, and it will focus more on its the foot side. And the second picture gives us an idea about how do these beams actually interfere. And if we don't give the right tilt, then what happens that either there will be a area which are not covered with any one of the beam coming from any one of the antenna, or it may happen that there are overlap, and that overlap will create kind of a inconvenience for users. And that's why finding out the right tilt is very much important. Next slide, please.
Next slide. Next.
So what we are doing here is that we are doing a little bit different thing. Before that, the quick view on the existing practices. There are two different ways. One is that the traditional way of tuning it by experimenting hit and trial. That's probably is not considered anywhere. There are mostly rule-based things. But there are some data-based approaches, like very advanced reinforcement learning-based approaches, but that has its own difficulties of more iteration requirement, high computational cost, and not only that, for sites which are very much new, for which we don't have any data, we cannot actually extend this. So the requirement in this scenario is a very light kind of application which can work on the limited data, can be accurate enough, may not be super accurate, but accurate enough, and which can easily scaled up for thousands and thousands of such mobile sites. That's how the RET, remote electrical antenna tilt optimization problem comes into picture. It's very much relevant. That's how it is. And what happens here is that the data science within which we have different ML and statistical modeling, that actually is being leveraged. We use past data. We study different antennas along with different types of covariates, its type, its the power that antenna consumes, and so many other covariates, and based on which we come a simple kind of prediction formula. So the whole problem here, the optimization of the electrical tilt is transferred into a prediction kind of or simple regression problem. Next slide, please. Now this gives us a very simple picture of why the modeling is so much complicated. In the left hand side, we see the average relation of tilt and coverage. As I mentioned, like a floodlight, if you increase up tilt, the coverage will increase, and otherwise, if you focus in the down tilt way, the coverage will decrease that way. So if you see the measurement of the tilt from vertical angle, then this tilt and coverage are inversely related. You increase tilt, then the coverage will decrease, and the other way around. This is observed at an average level, but at a cell level, when you go individual antenna level, we don't see that. There are a lot of noises, and there are a lot of reasons also, because individual antenna level, there will be different types of terrain. Some are vegetation more, some are vegetation less, some are water body, and due to that, there is no uniformity of this domain, fundamental domain rule. That's why when we want to predict something, we need to make sure that this domain rule is learned by the approach. Next slide, please. So what we do is that we translate the problem in our optical tilt problem. Mathematically, it becomes a regression where we actually minimize the different types of error, but here also there are certain problem with the errors. We just cannot take the normal error. On top of that, we need to understand that this fundamental domain rule of tilt and coverage, it requires a different type of error measurement. Due to some IVD restriction, I cannot go on detail, but when we formulate the problem, we take care about the individual cells performance as well as how much the prediction is valid. That means if now we have a tilt and coverage at a certain level, and we want to increase the coverage, my prediction of tilt should not be more, it should be less. And this way, that that kind of restriction we have to follow. So ultimately it becomes a way of doing the restricted kind of regression. Next slide, please. So what we do is that we do it in little different way. We very intelligently generate samples which will enforce the tilt coverage relations learning in the model, and thus it becomes a simple prediction problem after the proper structure of the regression being attained. And there are new metrics also we had to introduce, because these restrictions, they are not they are only being respected and they are only being reflected by different types of metrics. The general metrics are not informative enough in this case, and we had to do that. Next slide, please. So in short, I'll just say that there are pockets and there are fields in telecom where optimization plays very important role, and we need actually to make it very much scalable, because my understanding with telecom in last 3 years, what I have understood is the simple and simplest kind of solution also require this high scalability, otherwise it will not be usable in reality. And also that scalability in somewhere other instill the need of parsimony in all the approaches that we follow. So it should be like the model should not be unnecessarily complex, otherwise it will not be usable. And this probably gives us some different views, like optimization in a scalable way and in a distributed way. Those are the directions in which this application is sprouting in this telecom domain. With this, I'll say thanks a lot, and thanks for your time. Any question, happy to reply that.
Okay, thanks, Dr. Bandyopadhyay. Any questions from audience? Any question? Well, Dr. Bandyopadhyay, you didn't mention what method of optimization you are using it.
Yeah, so this is the optimization that we are using here is a convex optimization, because most of the objective functions that we come across with fortunately is convex. So we don't really go beyond simple convex optimization, at least in these two problems. But there are scenarios where we need to go for different types of optimization, like for example this genetic algorithm and others, where we know the problem is space is unbounded. For example, like same organism map and all those scenarios where we want network to learn by itself.
Actually, I think
for
your problem, the nature of the problem, I think it will be heuristic method will be better to represent.
It may be. Actually, it depends on the type of data you are getting. In some cases, we have seen that the data is too much of noisy, and hence we need to take care about that by cleaning up. And by doing that, many of the time we'll come across with a scenario where this optimization things will not converge properly. So maybe in those scenarios we can try those out, but at least in most of the cases we see a clear objective function, and hence the complexity is much less.
That is, you may not be able to express the closed form function in terms of variables.
Right.
Okay. Thank
in that
you.
Case, there is no problem.
Yeah. If there is no questions, let us thank to Dr. Bandyopadhyay again. Please join.
Thank you. Thanks, everyone.
Thank you.
Thanks.
Okay,
we come to the end.
Ends.
Yes, just 1 minute, sir. This session comes to an end now, and but the last event is giving of a memento to our session chair. Sir, please Just 1 minute. I request Professor Baswi Chakraborty to come onto the stage, and we would like to express our appreciation with a small memento. Okay. Thanks, madam. Thanks. Thank you, sir, for chairing this session. We come to the end of the sessions for today, and other sessions are being held on the 6th floor of ICT building, which is the next building. Thank you for your participation.